We could hear you.
No, it's not a AC voice, it's a projector voice. Projector voice. Just started, right?
No? Yes. Started. Yeah. No. Yes, Dr. Manas, please, you could carry on.
Okay, good. So first of all, I would like to thank the organizers for not only inviting me, but also allowing the concession to be not physically there. Otherwise, I would have carried the virus with me. So the second thing is that I'd like to also congratulate Dr. Sushmita. Sushmita Di, I think we met once in Calcutta, and it's amazing to see her contribution to the field as well. The other aspect that I would like to also point out that if you look at the speaker list for today's tutorial, I am the only odd man out with a physics background. And this is also a very good indicator that the field is actually moving more to engineering. And we call very often as technologists or engineers rather than physicists. This is a good indication that probably it's translating faster than it had expected. Way back in 2000, when things were still at the physics stage, people would not never believe that we have algorithms and discuss about designs. But now we are doing it. Another aspect is that I would like to correct also one thing that I am also since early this year, 50% of my time is at A-STAR Institute of Material Research and Engineering. And this is a very interesting aspect, which I will come to towards the end of what I will share with you. That material aspect plays a very important role, and that's the reason why in Singapore we started a fabless foundry just this year to speed up the development of quantum chips. Okay, I think I probably do not need to motivate you enough that quantum is very important. Quantum computing is very, very important in today, not just because there is a Moore's law and Moore's law is coming to an end. It actually has ended quite some time now, not because of the size, but because of the heat that it generates in a chip. So this is this probably slide which you have seen many times, and if you look carefully, there is already a kink here, and it will continue to happen. On the other hand, actually, quantum allows us to have algorithms which are not possible by classical algorithms at all. And the reason being, there are particularly two aspects of quantum which act as a resource for allowing us to solve problems which are otherwise not possible. And most important of them is superposition, that you can have superposition of states. It's not just 0 and 1, you can have both 0 and 1 with certain probabilities. The other aspect is entanglement. Well, it's a special type of superposition in higher dimensions where you cannot separate out the states as state of A and state of B. This inseparability is the root reason why quantum is used as a communication way of secured communication in today's QKD, or going ahead with something called quantum internet. Okay, but beyond those aspects, actually quantum algorithms have much more things to offer. And this will only be visible when we have large-scale quantum computers available. However, if we have a large-scale quantum computer, it also means that those computers should be able to give the right results with error corrections running on them, or they have to be fault tolerant, which means they do not produce error large enough not to trust the result. And of course, the holy grail of this is once we have such a big computer, now this such a big would mean even millions of qubits, we should be able to crack the RSA code. However, I must also mention that there is an archive article by a Chinese group very recently, like a week back, which claims to have modified the algorithm to an extent that you can break the current RSA code even with a smaller number of qubits. One has to see those results carefully though. Now, of course, there are two main parts of the quantum algorithms. One is the quantum search, the other is the Fourier transform. And there are branches from those. If you're interested in quantum algorithm, one place to look at is called Quantum Algorithm Zoo, where you can find more or less a full range of quantum algorithms currently available. So what I would rather concentrate on is the physical realization of a quantum computer. Now, if you look at this image, I guess I would not hear your reply, but I would like to know what is this? This is the ENIAC machine from IBM from 1945. This was the time when still vacuum tubes were used. Then look at this one. This is you would be very surprised to know this. This is a 5 MB hard drive. 1956. Now, if you look at this, you can then imagine what this could be. And most of you know this is the IBM Q, the modern day quantum computer. Of course, in terms of the size of it, it doesn't really matter because the quantum computers bring in a different set of computational abilities, which does not necessarily need to be at the laptop at the moment. Let's get into what does it mean by quantum computer. So we go one step behind. A quantum computer is based on units of information which are coded in a quantum system. It's again a two-level system. Two-level means it has two states. You can call it 0 and 1. Now, there are many realizations where you can find two-state systems. However, to find one which is quantum mechanical in nature, you need to really go to the fundamentals of particles. So these could be atoms, this could be molecules, this could be light particle called photons, or this could be a quantum circuit, just an LCR circuit, where you remove the R, go to superconducting state, and use a single microwave photon. So all these can be realized as a quantum bit or qubit. However, it needs to fulfill certain criteria, which are not so rocket science. It's the first one is initialization. So before we start any computing, we should be able to put all the qubits in the 0 state, whatever is defined as a 0 state. They need to have a long lifetime, meaning the qubit, that's a quantum phenomena, would usually decay from its excited state or to one state. But you should have a two-level system where the excited state lives long enough to perform meaningful calculations. The third one is that there should be a way by which we can quantum mechanically change the state of the system from a combination of one combination of 0 and 1 to another combination of 0, 1 in a controlled way. The fourth point is also very important, that at the end of the calculation, we should be able to read out what the output state is. And keep in mind, this output state, when we measure it, would be either 0 or 1, but with a probability, which means we have to measure it n number of times to learn about the probability. The fifth point is a very, very important point, and that's where a large part of the systems currently we have struggle with. That is scalability. Meaning I have one qubit and I want to make it to millions of qubits such that the errors as I make more and more qubits or add more and more qubits should not exponentially rise. As mentioned before, you can have all these properties in atoms, and then the platform is called an ion trap, or if it is a neutral atom, it is called atom tweezers. One example of ion trap, which is ion trap platform of quantum processor currently used is one example is that of IonQ, which is a startup from University of Maryland. The other example is Honeywell. While atomic tweezers are used by Pascal, a French startup. Then you have molecules. You can have molecules in optical lattices or ion traps. You can have optical photons. These are called integrated photonic circuits. Or you can have microwave photons. And then here you have superconducting circuits. This is LC circuit made of superconductors, or a silicon donor, where from a silicon you put an extra electron, and therefore you trap this extra electron, which acts as a qubit. The superconducting circuits is very well known because this is easier to adapt by companies. So you have Google superconducting qubit, you have IBM superconducting qubit, Rigetti, and so on and so forth. The silicon donor qubit is pursued by the Australian group and with Microsoft. Now here you get a little bit of glimpse of what are the important criteria that one should look at when choosing one platform compared to the other. On the left side, you see the kind of performance indicators of qubit lifetime, how long the qubit lives, the number of qubits demonstrated currently, the gate fidelities or errors, and this is an important issue which will be addressed in the next tutorial session. Then you have operating times, how long it takes to perform a gate operation, and connectivity. So the qubits may or may not be all connected to each other. There may not be physical wires connecting them. Now, if we look particularly at, I would bring your attention to the rightmost side, which is the NMR quantum computing, nuclear magnetic resonance quantum computing. This was one of the pioneers in the field. And in this case, the molecules are in solution, and the nuclear spin of the molecule act as a qubit. If the spin is up, it is 1. If it is down, it is 0. But this is an ensemble of spins, not just one single spin. I wanted you to look at this is that it is quickly known, quickly learned, people while doing the research understood that this system is not scalable at all. And therefore, this whole field is now abandoned. It moved to something else, which is a quantum dot. So this is one thing I think we have to be aware of, that as the platforms progress, it may happen that technologically, as well as from the physics point of view, it might be that we hit a bottleneck which cannot be removed. In that case, one has to abandon and move on. The other aspect I would like to also look at is topological. These are perceived qubits. Certain materials may have this property, which is theoretically known, that they're protected against environmental noise, which means there won't be any error in them while they're manipulated. However, till date, there is no such material being produced in the lab. So this is, again, one has to be very mindful about, like what wants to achieve in a long term, and what is currently available, as the number of qubits are in the range of hundreds. So from the current knowledge we have, The superconducting circuit qubit, the ion trap qubit, and the photonic qubit have shown to be scalable to the extent that we currently have in hundreds of qubits. There is the announcement about 433 qubits from IBM. One has to see the error rates in them and so on. But on the other hand, if you look at roughly the number of operations one can perform, which is a ratio of the qubit lifetime to the operation time, meaning you have a qubit which lives for 100 of microseconds, while each gate operation can be done in 50 nanoseconds. You can divide these two numbers to get roughly 1,000 of operations that could be done. And if you look into that, both these platforms, as of now, shows similar possibilities. The other difference that you see is the fidelity of the gates. This tells you what is the error rate in each gate operation. And these, at this point, for the ions, are still the leading ones in terms of how good those can be manipulated. And there is a reason behind that, why they are better, is very easy to understand. That the superconducting qubit, we will see in a minute, are to be manufactured in the lab by lithographic means. Now, this is a kind of a man-made atom, while in case of ions, you get it from nature, and so no two ions in the world would differ from each other. So they're absolutely same qubit everywhere. And that's one of the fundamental reasons why the accuracies or errors are little in case of ion traps as compared to the superconducting. Okay, let's move on to the systems. If you look at these two particular systems, which I would concentrate a little bit more, is this left one is called the superconducting circuit qubit. What you actually see is a dilution refrigerator. So it may look very complex, but at the end of the day, this is a standard technology which brings the temperature from 300K to 20 millikelvin. So it's very close to the absolute zero. And but this has nothing to do with the quantum computer. The quantum computer actually is a chip which sits at 20 millikelvin. And the rest is microwave engineering, where you apply certain microwave pulses and read out certain microwave pulses. So there are certain technologies, and this I want to emphasize because this is a VLSI conference, and therefore it is very important to understand that even though we are talking about quantum computing, but the technologies that go are very classical. So you have microwave engineering, we have cryogenics, and we have microwave engineering for superconducting circuits. On the right side, this is more atom-based, and in this case, the technologies that go in are vacuum technology. You need RF, radio frequency, optical technology, and a part of cryogenics and what is called trapology. It's basically how to design better and better electrodes to confine atoms. Okay, so let's look into what does a superconducting circuit actually mean. It's a very simple circuit. It's a L and a C, so a inductor and a capacitor. And we know that this would be like a oscillatory circuit where the charge will go back and forth between L and C. In quantum mechanics, this behaves like a harmonic oscillator, and it says that it has many energy states, and each of them are equally spaced. Meaning, if I say this to be 0, this to be 1, 2, 3, all of them are equal energy needed to move from 0 to 1, 1 to 2, 2 to 3. Which means we cannot use it as a qubit, as we discussed before, that we need to have a unique two-level system where two of these levels have energy gap, which is not same as any other energy gap. To do that, you need a special type of L, which is a nonlinear L or Josephson junction. A technical term is a tunneling junction. which creates this nonlinearity in the harmonic oscillator, and therefore now you see the lower two states have different energy gap compared to any other states above. And once we have created that, we can actually use this as our qubit, 0 and 1. Now, there is ongoing research capabilities people are trying to develop is to also use the higher ones as higher dimensional quantum systems, not a qubit. Now, let's look into what this junction means. It's nothing else than a nanometer scale metal oxide metal junction, and this junction behaves like a Josephson junction, and that's what we need to make in the laboratory. Once we have made that, this is what you see here. You need a cavity which produces the capacitance and the resonator that couples to it, and that's your qubit. So the left side is actually your Josephson. Okay, for the case of atoms, it is simpler to understand. On the left side is the external field that is used to confine the atom. So in terms of the qubit, this has nothing to do almost. The left side has nothing to do with the qubit. The right side is the internal state of the atom, and that's what we use as qubit. So for example, out of all these levels, we actually choose whatever this ground state is and this 5D half state. These two states we choose to be our qubit, while as you can see, these are the wavelengths that they couple, and they're all different. So we are very easily can choose by choosing a particular laser only these two states as our qubit. And if we do that, we have also very long lifetime. This state does not decay till 30 seconds, which is considered to be very long. And on the left side, you can see if you confine such a number of ions, in this case about 40 ions, each of them is a qubit having these energy levels inside. So now what you need is you have the qubit, you need some gates to operate on them, and then you can write your algorithms. That forms the whole process of performing your quantum operations. Like the universal gates here, in the classical case, we would call it a NAND gate. In case of quantum, it's a controlled NOT gate between two qubits and any universal rotation in a single qubit. This comprises the universal set of gates. Once we can perform these two, we are ready to perform any algorithm. So these are again the same thing as I mentioned, the 5 criteria. They have a name, the Vincenzo criteria, based on this paper in 2000. Now I will get into a little bit details about how the initialization is done, which is, for example, we have chosen now this and this to be our 0 and 1. So there are ways by which you can apply a laser field, and if you apply a laser field, this will decay into both these states. So if you keep on applying this laser field, after some time, all the population will end up in 0. And that's called initialization in case of ion trap or any atomic qubit. For case of superconducting qubit, it is just by the temperature being so low, there is no thermal activation to the higher state. So by cooling down the chip, you achieve the 0 state. Then the next thing is the coherence time, as mentioned. For this state, it leaves for 30 seconds, which means you can have your operations done within 30 seconds without seeing a decay. In terms of qubit coherence, one could actually look into, there are two aspects to it. One is how long it takes the qubit to decay. The other aspect is that the qubit may not decay, but it may dephase. Now, what it does dephase means? D phase means that if you with a qubit, which is a superposition state like 0 and 1, where A and B are complex numbers, I can write the complex numbers in cosine and sine like this. Then what happens is that this qubit, if I allow it in this superposition state and leave it without doing anything, due to external noise, this state after some time starts to dephase, meaning acquire some noise from the environment, and hence will also lose information. So these A, B's could be then changed to something else, and therefore the probabilities will change. So these have technical names. One is called a T1 time, and the other one is called a T2 time. T1 time is the current time that ultimately you can achieve, but T2 is more restrictive. So then goes to the quantum gates. So the single qubit gate is simpler to understand, and you will restrict to that only. In this case, what you do is you apply certain laser pulse for certain amount of time, and this time is shown here in microseconds. What you see is the probability of the state to be in 1 as a function of this time of application of the laser. And we can see if we stop the laser, for example, somewhere in between, we can produce an equal superposition of 0 and 1, roughly about 10 microseconds. So this gives you the idea that you can rotate the qubit state. When we say rotate, it means rotate in a complex Hilbert space. And any kind of rotation is considered to be universal, because with only by 2 non-commutative rotation, you can make any arbitrary gate operation on a single qubit. As for example, if you wait long enough, you would reach full 1, or if you stop somewhere, you would reach equal superposition states, and so on and so on. For a 2-qubit gate, which is a CMOS gate, the most popular one is called a Mollman-Sorensen gate. I don't want you to, but roughly speaking, if you look at these blue and the red lines, these are lasers that link them, and blue and red denotes 2 different colors. If you choose any path with starting with a blue and going to the red, you would end up in the same state for both paths. If I take this path or I take this path, I in both cases end up in the same final state. The intermediate paths are cancelled out, and this is called interference effect within the qubit system. And if you look carefully, the marking of the systems, there is no 1 ion but 2 qubits. First one is in the ground state, second one in the ground state, and that's how we represent them. Now, by applying such bichromatic pulse, you can generate a CMOS gate. Therefore, we have shown that you can produce any single qubit rotation, you can produce any 2 qubit rotations, and therefore you can perform any kind of algorithms with these qubits. Last part 1 is the measurement. So how do we measure? Either the state is in 0 or 1. If it is in 0 state, you see it will give a fluorescence if we apply this blue laser here. And this is a real image of an ion taken on a CCD camera while this laser is applied. This is if the state was in D state, then even if I apply this laser, which is actually applied, we see nothing here. So that would be our 0 state. We can do this for 2 and even more. Therefore, you can build up your final states by just looking at the CCD camera. Of course, we don't look at, these are fully automated. Compared to the superconducting qubit, one big advantage for the ions is that your efficiency of this detection is has an error which is below 1%. Okay, this is a rough sketch of where the different technologies stand. it may not be completely accurate. It stopped in 2020. But again, one has to see this comparison may not be complete because this does not include the error rates and so on. But one could think of this as the years progressing, there is a tendency of increasing number of good qubits coming up. Now let's go into the critical problems that we face. This is from one of our colleagues, which the chips is developed in our foundry. You can see the coherence time as a function of how long the qubit is operated. This is for 16 hours. And the T1 and T2 time shows you fluctuations that are unaccounted for. You perform full gate and kind of a truncated Gaussian sums. You see the noise here. So these are the right results. And this is the threshold. The noise here are pretty high. For the atomic qubit, the problem comes from like roughly to one of the classifiers that we have demonstrated. And in this case, it's a, if you look at the classifier in a simple term, it's a machine learning problem. We start with either 0 or 1, and we train the machine, or in this case, the qubit, such that all the class B are driven to 0, all class A are driven to A. Once trained, we then look into the outcomes. And this is some of the boundaries which we can separate out. On the left side is a simulation, and this is on the real quantum computer. We can look at more complex ones, like the non-convex. But for, you can see here, the problem that we face is the red dots are where the simulated results are, and the blue one, minima, are where the experimental results are. So there is still some error between the simulated and the actual minima. As a next stage, we can summarize that there are issues with the superconducting circuits, particularly related to material and processes. For ion traps is the interconnects. And for this, we started recently the quantum foundry in order to address these problems. And we collaborate with Tektronix in terms of characterizing the qubits. I think my time is kind of up. So in terms of what we can do currently are develop these chips. We can produce 3 to 10 superconducting qubit chips, as well as ion trap chips within the foundry. And I would like to acknowledge the people who work with us, and most importantly, our team. And we always look for good people. Thank you.
Thank you, Dr. Manas. The last one? Yeah. Okay. This is the older one?
Doesn't matter.
Okay, sure. Okay. Let me just share the screen.
ఇక్కడ నుంచి ప్రజెంట్ చేయాలి ఇప్పుడు
ఇక్కడ చేయండి.
సేవ్ చేయండి
Yeah, actually, when we share it, his sharing will be gone.
You can start. You can ask to stop sharing.
Yeah, I think Manas stopped sharing. Now we
Without
could.
stopping.
Huh.
No, it's not going. You need to stop.
No, this is our presentation now.
This is our presentation.
Now we need to share this.
Okay. Hello. Yeah. So can you hear me? Okay. So what I'll cover today, you heard about quantum error correction, quantum algorithms. Dr. Manas mentioned about the fact that superposition and entanglement can give us power in the quantum computing that we are after. The reason are twofold. One is the limitations due to Moore's law, as you heard about. The other is algorithmic limitations. There are certain problems for which we get exponential or super polynomial speed up in terms of time over classical computing. So let's look at how these algorithms work. Okay, how many of you have seen some of the quantum algorithms? Can you just raise your hands? Okay, okay, so that's good. I mean, most of you, it's going to be a tutorial, so I'll go slow like a class. Okay. So you saw, Dr. Manas talked about classical gates, such as NAND gates, and he mentioned about quantum gates like the CNOT gate and the rotation gates. Okay, so here are some what are known as the quantum gates. So this is a single qubit gate, and the way it's represented is in terms of a unitary matrix. Okay, why a unitary matrix? So if you have a single qubit, a binary system, and you have a single qubit input, it could be either in the basis states could be either the 0 state or the 1 state. So the input qubit, either 0 state or 1 state, and the output, if you measure, would be one of the along these. So this gives the probability that you will get if you feed 0 as the input, if the input is a 0 state, that means the qubit is in a 0 state, and you apply this rotation operation with an angle of theta, rotation of angle theta, then the probability that you will get the 0 state is cos of theta by 2. And the probability that cos square of theta by 2. And the probability that you will get the one state is sine square of theta by 2. So you have two combinations for a single qubit, the pure states, and two combinations for the two possibilities for the output pure state. And this entry here tells you what is the square of this will give you the probability with which after you perform this operation, what is the probability that you will get this output. So this is for rotation about the x-axis. So you can think of the whole continuum of possible states as a unit sphere. It's known as the Bloch sphere. The North Pole is typically represented as the 0 ket or the 0 state, and the South Pole is represented as the 1 ket or the 1 state. And the entire sphere, continuum of it, represents states. However, this is a special kind of state space in the sense that you can represent this entire state space with a finite number of what are known as basis states. So this you can go recall your vector algebra. So a vector space can be represented by a finite number of vectors. So any vector in that space can be represented as a linear combination of the basis states. So therefore, what you can get by performing these operations, so in the sphere you can think of it as x, y, and z direction, and therefore you can perform rotations about those axes, and this is the parameter about which, so you can see this is any value from 0 to 2 pi, any real value. So you can have a whole lot of states there, but if you measure, then it's going to collapse to one of the basis states, and the probability with which it collapses is given by the the operation defines the probability with which it collapses. Okay, so these are 1 qubit operations. All of these are 1 qubit operations. If you have an n qubit operation, because you will have with n qubits, you will have 2 to the n combinations of the state space represented by binary strings, and 2 to the n in the output, you will have a 2 to the n cross 2 to the n matrix representing the operation. These for the inputs and these for the outputs. So the entry there represents, if you feed this input, which of the outputs is what you get is the corresponding entry over there. Now, I will point to these gates here. These are known to be fault-tolerant gates. You heard about error. Quantum computation is very fancy, very attractive because it can do a lot. It can give you exponential speed up, but everything comes with a cost. It's fragile. It's very error-prone. Okay, and you see, you heard about this qubits. Okay, they are whether you have electron spin, or you have atoms or photons, or ions, they are supposed to be in a closed environment. Only then can the state be retained. If there is some interaction with some external world, then it is as if some operation is being affected on the state, and the state can change. Now, interestingly, you saw a particular picture of a quantum computer. And okay, I'll get to that. Before that, let me just point out to this particular one. I don't know whether you can see the H. H is a very important operator. It's known as the Hadamard operator. Here it's a 1 qubit Hadamard operator. And what it does is that superposition, equal superposition. So if you have a qubit in the 0 state, let's say, and if you apply Hadamard operation to it, it will convert it to a state which is equal superposition, a linear combination of 0 and 1 with equal probability. Okay, so that's the Hadamard state. And if you apply this in parallel over all the n qubits, then you have all the 2 to the n combinations with equal probability. That's a very, very important operation that is used in many, many quantum algorithms. Now, what does a quantum algorithm do? Okay, the whole purpose is to, just like an algorithm, just as in classical algorithm, you have a sequence of instructions. You may have some branches. Let's consider a deterministic algorithm. You have a sequence of instructions followed one after the other. You feed some input, and after each operation, there is some change in the variables that are involved in the program, depending on the input that you supplied and the particular operation that you are doing. Okay, and at the end, after a sequence of operations, at the end you have one of the variables which will have the value corresponding to the correct output for the problem that you're solving, and the input that you've given to that problem. Now, in quantum algorithm, I've been talking about electrons and ions and atoms. Then how will I do, factorization, which are integers? Okay, first of all, you have to do encoding, as we do in our chips that we have. It's encoded in digital binary zeros and ones. That is basically voltages. Okay, so in classical, it's the voltages, the voltage level. If it's above a certain threshold, you call it a one state, value one, and if it is below, then it's value 0. Okay, and you keep on applying your operations like add, multiply, what have you, and all that. Here, what happens is, again, you have the notion of state of a particular qubit, which is a basic unit of information. And when you are applying these operations, so what does applying an operation mean? Here, you are actually applying electromagnetic pulses or fields to create the change in the quantum state. Okay, so therefore, the quantum algorithm is a sequence of such operations, and corresponding to that, in the real computer, you would have to program the control circuit to apply those electromagnetic pulses, and you gradually, over a sequence of operations, bring it to a state which corresponds to the encoded version of the state corresponding to the correct output. With, of course, there's a caveat there, with very high probability. The quantum computing has a probability associated with it, and that is why you may have to repeat the experiment to take the measurement. Okay, so these are so the previous ones were 1 qubit gate. Here is the CMOS gate that Dr. Manas talked about. So you have for 2 qubits, you have 4 possible combinations. So this was the circuit that you saw. This is known as a control qubit, and this is known as the target qubit line. So if the control qubit is 0, then nothing happens to the target. If the control is 1, then the target flips and the NOT operation happens. So that's the CMOS operation. There are similar other operations, and the corresponding matrix which represents the combinations, the correspondence. Classically, you were familiar with the truth table. Here, it's represented as matrices. And the reason is that, I'll just digress for a minute, that is, quantum computation is known to be reversible. What does reversible mean? That by looking at the output, you can uniquely say what the input is. For the NOT gate, it's possible classically also. But for the AND or the OR, it's not. Because in the OR gate, if you see a 1, you don't know whether the input was 0, 1 or 1, 0 or 1, 1. Right? Similarly for AND. So classical AND and OR are so-called irreversible. But you can convert them to reversible. You need some extra inputs and outputs. And one condition for reversibility is that the number of input bits should be equal to the number of output bits. And so in the input, you have all possible combinations. The output should be, you should have a 1-to-1 mapping. That means basically a permutation of all the states here, so that by looking at the output, you uniquely know it's a permutation. So you uniquely know what is the corresponding input. That's the basic mathematics behind reversibility. So all of these are reversible. Yeah, you have a question.
It is like I've heard one statement like in the book that when you look at the qubit, its state, it's a fixed, like it is one of the. And when you look at it, its process is disrupted. But when you don't look at it, it's just.
Yes.
I don't exactly understand what I mean.
Means whenever you measure. Okay, so this is the famous basis for quantum mechanics. Okay, that this is the uncertainty principle. That is, you either know the position or you know the velocity, but if you try to measure one, the information about the other goes away because it has already moved. Okay, so it's something of that idea. So here also, if it is in isolation, it remains in that state. But the moment you measure, there is an interaction, then it collapses to one of the states. Okay, it could have been in any of the states, any of the combination states, but it collapses. But that is where the probabilities come in. It just doesn't randomly collapse. It depends on where it was. That is, what was the particular combination it had. And depending on the combination, the probability changes. Okay? I hope I've been able to. Yeah. Sorry? Yeah. Measurement and initialization are major issues in quantum computing. Okay? Yes.
physical states.
Right.
It's possible. But how we can measure from physical, can convert from physical to quantum states?
Sorry, from?
Physical to quantum state.
How do we do the initialization?
No. When we are measuring from,
from quantum to physical.
Yeah, quantum to physical is okay.
Yeah.
But from physical to quantum, is it possible?
We do encoding.
Okay.
We do the initialization or the encoding.
Yeah.
Okay. Okay. Swap gate is another important gate. I don't know, this got moved somehow. Anyway, this means that whatever is the value here will be here, and whatever is the value here will be here. So it swaps. Now, yeah, let's go on. So these are some more. So quantum circuit looks like this. So you have some qubits here, and this is a C0 operation. This is an X operation on the first qubit. This is a Z operation on the second qubit. The reason I bring this up before I get into algorithms is because you will often see such things which are known as quantum circuits. These are schematics. They seem to be like our electronic circuits. But I should tell you that these are not wires. This just represents the sequence of time. So in the quantum computer, you won't find any wires. Everything is done wirelessly through electromagnetic pulses, okay? Field interactions, okay? All that you have is a qubit here and a qubit there, and depending on what kind of pulse you use, will the particular operation happen, okay? There is time which is needed. You saw that chart in the previous part. To operation time, and there is also some probability of error in the operation. There's some probability of error in the quality of the qubit that you create. All that is going to affect the correctness of your output. Okay, and so when you are designing quantum circuits to realize some quantum algorithm, here are some metrics. You want to minimize the number of qubits, you want to minimize the number of quantum gates, and also the time required, because there is a lifetime of the qubit before which the state is going to become corrupted or it's going to change. So all that actually comes in the design automation part, which will follow here. Okay, let's. Sorry? This is a notation. This denotes that this is going to be the control and this is going to be the target. This is just some notation it is for. Yes. No. That is Rx and Ry. X is, okay. So these are related to that. Yes, you are right. Okay, but slightly different. Okay. So these are related to that. These three gates are also important in error correction. These are known as the Pauli gates. Okay, we'll see that. Which one?
Initialization of the circuit. Initialization state is not from how you do it.
Okay, so I want to bring this to zero ket. Okay, so you typically most algorithms start with zeros, all zero state. Okay, that is for the technologists to talk about. Okay, so I think I'm not an expert on that area, but essentially what you do is you apply a certain pulse so that so basically you want to apply, let's say, Rx0 and Ry0, or Rx0, Rz0, two operations, so that there's a something like that. Okay, depends on. So even initialization is not trivial. I mean, I sort of hand waved, but it's not trivial. It's also a major research area. Okay, now let's get to algorithms. It's only 10 minutes and I haven't even started on algorithms. So, okay, let's look at the first algorithm. Okay, just to give you an idea what quantum algorithm can do. Okay, so the first problem that was solved by Deutsch. So the Deutsch-Joshua problem is like this, that you have a Boolean function. The input is an n-bit string, and the output is a 1 bit. Okay, so this is how it's a non-reversible function, as you can see. And you are also, it's a black box function. You're not given the function. All you're told is that it's either a constant function, that means for all possible inputs, it's a constant value, one of the two values, or it's a balanced function, meaning that for among all the inputs, for half of the inputs, it is 1, and for the other half, it's 0. Which half you don't know. Only information is this. Now, classically, what would you do? You have 2 to the n possible input values. How many function evaluations would you have to do? You can do it slightly better, right? You don't need to go to 2 to the power n. You need to do half of them plus 1, right? If the last one is same as those half, then you know it's constant. Okay? So anyway, it's exponential. Dawes showed that you can do this with constant time. How did he do that? Okay, so actually the first algorithm he took was with 1 bit input and 1 bit output. So classically it needs 2 evaluations. Now quantum, he showed 1 evaluation. So people said, oh, what's the big deal? You know, from 2 to 1, what's the big deal? And then he quickly, in a few years, he showed it from 2 to the n to constant. Then also people said, yeah, that's something. But in the meantime, Peter Shor had come up with this fantastic factorization algorithm, and because it was related to the crypto system, everybody shook up. And so this is basically how if I have 2 qubits here, then there are 4 possible outputs. Okay, no, if I have just 1 bit input and 1 bit output there, and I know that f is constant or f is balanced. F is constant means 2 possible f, right? Either f is 0 for both the inputs, or f is 1, or it's balanced means f of 0 is 0, f of 1 is 1, or opposite. So there are 4 possible such functions. Okay, and you need 2 evaluations in the case of classical. In quantum, okay, so if this is kind of circuit that I have, what is this operation that I need to do? These are not very clear, but anyway. So let's say first I set both of them to zeros, okay? And I add a demand operation on the first qubit so that this becomes equal superposition. And then I feed it to this black box function over here in such a way that this is the output that I get. And what do I get? So the operation is in the reverse order. This is identity, this is Hadamard, and if it is independent, you usually take the tensor product of the 2 matrices, and then you apply, then you multiply with the matrix over here. It's in the reverse order. And the input was 0 here and a 0 here. The output is equal superposition, so you don't know anything, no information. Probably, if you measure, is with probability half it'll be 0, probability half it'll be 1. No good. So this setting is no good. What about this setting? I put 1 over here and I add a Hadamard out here, and then I do this. So this is the operation that I am doing. Here also, I don't get any information. Okay, I can't say uniquely what is happening, but there is some indication that the value of the function is appearing as the sign of the entire thing. So putting these two together, Deutsch said that what if we did this? Set this to 0, put a Hadamard here, set this to 1, put a Hadamard here, and then again you put a Hadamard over there. Then what you get is that if f is constant, then you will always measure this to be, the first qubit you measure will be 0. If it is not constant and balanced, then it will not be 0. So that is why in one step you could say whether the function is constant or balanced. Okay, that's the idea of Deutsch's algorithm. So I'll skip all this. So the first operation, yeah. Sorry? Yeah. So the first, the 2 important things from this, the takeaway is phase kickback, that means the value of the function, instead of evaluating this, that is, it could be it's 0 or 1 because it's a one output, 1-bit output. It is converted to the sign of the, so the phase of the, so the amplitude, the value is, output state value is converted to the phase value. Okay, that's known as the phase kickback. And of course, Hadamarding, so that at one go you have all the equal superposition. Okay, so this was the thing, and this is, I have already told you. So exact classical query would be this much, and exact quantum query would be 1. So this is what separated the kind of problems which could be solved by classical deterministic polynomial time algorithms and quantum polynomial time algorithms, but this has a probability associated with it. Yeah, things are getting there. I mean, when he invented in 84, there was nothing. Okay, but now you actually can simulate them and also run them. I'll come to that. Okay, if Anupam permits. Okay, I haven't even. So this is another important algorithm, the Grover's algorithm. It's unsorted list, and given a particular state, you want to find out whether that is over there. And the idea is something like this. So suppose you have a list over here, and this is the one that you're searching. What you do is, first you somehow you devise, based on this, you devise the operation in such a way that the value corresponding to this gets inverted. You take the average and you deduct the average from all of this, then this is what the state gets. You negate again, and after that you see that the value here, the value corresponding to the correct output is getting bigger and bigger, and the others are decreasing. So that's what we are going to, so that when we measure the probability that it will, if the given key is in the list is very high, it will give the correct output. So here now you construct that. So here is the rotation, that means it's negated. And here is what is known as the averaging and subtracting from the average. So this is the one which is increasing, the others are decreasing. So basically you have to keep doing this. How many times? That is what is important. And that was shown that you could actually do this in square root of n. So classically you needed order n. Here you don't get exponential speed up, you get quadratic speed up. Okay. The last algorithm I'll talk about is Shor's algorithm. This is one of my favorite. This is a 170 plus digit integer, which is the product of these two large integers. Okay. You can multiply them and get this very easily, but to factorize this is not easy. And classically, it would need so much, this is a time complexity, depending on the number of digits, this is the amount of time you would need. Shor's algorithm gives polynomial time. And the idea is very simple, it's middle school. Okay, I just want to share the idea, I won't go into the quantum part. So suppose I want to factorize 21. What I do is, you can easily test in classically in polynomial time whether it's a prime number. Our own Manindra Agarwal, Neeraj Kayal and Nitin Saxena designed this, and you can do that in polynomial time. You can also check whether it's a prime power. If it's an even number, all that you can check. So you're left with something which is not a prime power, not an even number. So it must be having some factors. Now you choose another integer which has GCD 1. It's relatively prime. The GCD of these two are 1. Now it's a very old number theoretic result that if you do 2 to the j modulo the number n here, if you increase the j's, then the values that you get here is going to be periodic. Okay, let's call that period r, which means there is some r for which x to the power r modulo n. What does modulo n means? That you divide by n and whatever is the remainder is going to be 1 for r. Let us call y to be x to the r by 2 modulo n. Okay, so if here r was 6, So y is r by 2, 3. So y is 8. Now, if you take the GCD of 8 minus 1 and 21 and 8 plus 1 and 21, you're going to get the factors. That's something very easy. We did this in middle school. So why couldn't we do it? I mean, why did we have to wait till 1994? The catch is finding R. Okay, finding R in polynomial time. Classically, it went into exponential time. Schur did it in polynomial time. Okay, I'll skip it. He made use of something called Fourier transform, discrete Fourier transform in the quantum domain. So before Fourier transform, he was just selecting out certain states which were R apart. These are the numbers of the states, if you know. And then you convert them and you measure. Sorry, I have to skip. So initially you had 512, that is 2 to the 9. And then after you do, you get the periodicity. So only the periodicity here is, I think, 1, 2, 3, 6. So you have these in 6 groups, okay? And then somehow only certain things, if you do the, you can group them into 6 parts before DFT, and after that the probabilities increase for those particular states. You measure one, and which one you get, you can do this a few times. Then from there you can find R in polynomial time. Please go back. I've just given you the idea. Please go back and read about it. Okay. Now, just 5 more minutes, if possible. I said it was very fragile. So without error correction, we cannot actually depend on the results provided. Okay. So here is the classical qubit and the quantum qubit. And let's say you have a state like this, and the corresponding circuit is like this. This is an entangled state, actually. These are some of the gates. Now, if you run in a simulator, you find that because it's there are two qubits, 4 possible inputs, but the state was such that it's either it's equal probability for 0, 1 or 1, 0. So if you measure, if you simulate, you will find that each of them have probability half, almost equal. But if you run on a machine nowadays and they are noisy, you'll find significant, less, but significant probability of getting wrong values also. So that's why noisy machines need error correction. Okay. Now, error correction is there in classical domain also. Okay. What you do is you repeat, over the channel if there is but the challenges in quantum error correction is if you measure something, you can't reuse it. The superposition goes away. And another important thing is that in quantum, you cannot copy. Copy means read and then write. Read means measure. So it collapses. And how can we correct multiple types of errors? Okay. So I'll skip this. So what is done is you don't measure the original information qubits. You use some extra qubits, and you use some operations in such a way that if there are errors here, then the values of this that you will measure will tell you whether there's an error. Okay. So the first bit of error syndrome, this is the error syndrome, says whether the first 2 bits are same or different. Okay. And the second bit tells you whether the second and the third are same or different. So by looking at the error syndrome, I would be able to tell on which bit there is an error. So logically, we had 1 qubit. Physically, I'm replacing or representing that 1 qubit by 3 physical qubits and adding some extra qubits, which I can measure for checking whether there is an error. And if I can uniquely decode this error syndrome, I can go back and correct. Okay. So if I have 010 or 101, all of them will have syndrome 11, which means that the second bit is different. So you can flip the second bit and get the correct back. Okay. So this is actually redundancy, not repetition, which would need copying. Um, all this has got mixed up. And similarly for phase errors, it's easy because if you do Hadamard, the bit and the phase becomes sort of synonymous. Okay, so you can do the same thing over here. And moreover, the Pauli group, remember, if you can correct, if you have an error correcting code which can correct errors on these three, then it can correct error, any kind of error. Okay, so all error correcting codes actually are like this. So the entire Hilbert space of states are over here. So initially you had, let's say, k number of qubits in your algorithm, but you expand that, like in classical coding theory, to n greater than k. Okay, you have a larger space. And so these are invalid states or invalid code words. The valid code states are over here. So with an error, it's going to take you outside that. And if you can detect that it's outside, then and you know which one, then you can go back. Okay. I think I'll skip all this. Some codes are Shore code, the one that I talked of, Steam code, Laflamme code. Basically, what you're trying to do is you're trying to find a group of operators such that, when you apply that operator, it will, if the no error has occurred, then the phase will remain +1. If error has occurred, then it will become -1. Okay, that is the, the main thing. So for short code, this kind of a circuit. Imagine error correcting is very expensive. For a single qubit, you need so many 9 qubits, so many gates. That's why today we have about 127 or 433 qubits. With that, how little can you do? And then if you want error correcting in it, it's not possible yet. Okay. So another thing is we had all these C0 problems. So C0 means between two qubits, which should be close by because these are electromagnetic couplings. So if you have a C0 like this, you actually have to bring them closer first. You have to do a swap operation. And that again leads to time and space and resource. So therefore, you want to, this is known as the nearest neighbor problem. We had been working, Omlan in his PhD thesis had done quite a bit of work on that. So to overcome that, some more codes were invented in what is known as surface codes, and which is actually in place now in most of the. So it is in a 2D. So the nearest neighbor is just not just linear, but in a 2D fashion. Okay, in a lattice form, and basically you have. I think I don't have. So the pink ones are for the parity of the qubits. Okay, so if there is an error, then you know what operation to apply to correct it. Okay. Now we are moving from this kind of a square lattice to what is known as a hexagonal lattice. Okay, which is known as the heavy hex code. It is supposed to be more robust. Okay, so distance of a code means what is the number, what is the distance between the code words, that is how many bits can you correct. Okay, so distance D code corrects D minus 1/2 errors. Okay, I'll skip all this. You have not only binary systems, you have ternary systems. We have done quite a bit of work on this, trying to propose new error correcting codes. So the key takeaways are these: superposition and entanglement provide exponential speedups. You heard about this, where you can get all the algorithms still today. And because it's error prone, you will need error correcting codes. At present, these are noisy. So with the noisy intermediate scale devices, we can't have the exact quantum algorithms operating and giving us exponential speed up. What we can have probably is quantum approximate optimization algorithm. Some of them have been proposed for not only combinatorial optimization, but for also quantum chemistry and other kinds of simulation. Omlan will talk a little bit about QAVAs. Thank you. I ran way over time. Sorry about that. I think we'll have questions at the end.
Thank you, Dr. Sushmita. So we will just take a short break for 5 to 10 minutes. I know we are already running late due to the technical glitch. So please bring your, maybe what you could do is you could just get your tea or coffee and snacks back to your places. Yeah. So we'll stop here and we will start in by 3:30, 7 minutes. Okay. Dr. Manas and Dr. Robert. So we will start in the next 8 minutes. We will be taking a short break.
Thank you.
Yeah, all right. Thank you. Yeah, sure. We are going to start now. So all of you, can you get back to the seats? I'll just go out. Maybe. I don't know.
The people can come and join. I want to start now. Okay, welcome back everyone. So sorry to interrupt your interesting discussions in between, but we are running a bit late with the sessions due to the technical glitches. And now we have a second part of the talk after we learned about different algorithms and technologies we come to the application side, like why we at all need quantum computers. And one of the biggest motivators for the quantum computing application is cryptography that I will talk about now. So if you look into security in quantum era, that is one of the biggest threats being posed by quantum computers, a large one of quantum computers. So the first question is whether the threat is real or not, and by when we can expect something that will disrupt the security protocols. And then I will talk about some of the recent results in quantum enabled data that we have been doing. So this is the paper that already Susmita mentioned about in 1994. In 1994, Peter Shor came up with the algorithm which directly brought down the complexity of factoring and discrete logarithm. These two are known to be the computationally hard problems and the basic building block of RSA and ECC cryptographic systems. So RSA and ECC are the ones which are basically fueling all the public key protocols that we know now. So be it the e-commerce, be it the TLS or IPsec protocols, your online payments, the payment terminals, everywhere, a basic key exchange or digital signature that is running. And in those protocols, we assume that factoring is hard, discrete logarithmic is hard. Hard means with a classical computer, it will take billions of years to find the solutions. And with a quantum computer, we can do it in the matter of hours. And that is the biggest threat to the security protocols that people get worried about. So it's not only about the quantum computing community, but it created havoc in the security community as well. So people who are cryptographers, they need to figure out what to do with the advent of this new quantum computers. So Shor's algorithm showed that RSA and ECC can be broken. There are already practical demonstration of factorization in very, very small scale though, like the example that Susmita very nicely presented, that you can factor 21. So since then, larger and larger factorization have been shown. It's not yet practical threat at this point, but this capability of a quantum computer to factor and find a discrete logarithm, it's growing over the time. And there is another bunch of cryptographic algorithms that we call as symmetric key cryptosystems, which we use for simple data encryption, block ciphers and stream ciphers like AES. So there is also a range of quantum algorithms that people are developing in order to attack those cryptographic algorithms. So both public key and private key, asymmetric key and symmetric key, both of them have some threats from quantum computers. So how realistic those threats are and what kind of alternatives do we have? So some simple back of the envelope calculation. So the largest RSA, Reves Shamir Edelman, factored in a classical computer is 768-bit. And in order to prevent our secrets, sensitive data, what we use now is RSA 2048. That's 2048-bit long number that we have to factor. It was shown with an empirical calculation and a bit of simulation that using 20 million noisy qubit quantum computer, you can break RSA 2048 within 8 hours. Okay, and right now, as you know, we are in the 400 something qubits. So the calculation also takes into account that modular exponentiation, one of the building blocks of this factorization, is the most complex, which requires a depth of 2000 n square and 9n plus 2 logical qubits, where n is the number of bits. It includes other blocks. It includes quantum error correction and needs a logical to physical qubit mapping. So due to this error correction, in the world of qubits, one logical qubit can be translated into thousands of physical qubits. So you cannot assume that just one qubit or 400 qubit is sufficient. So if I take all these calculations together, it actually leads to this very big number. So we can wait for a while. The 20 million noisy qubits, it will take few years, if not like a decade, to mature enough to attack RSA 2048. So this is where we are right now. And if I look into the other spectrum of private key or symmetric key cryptography, then the basic idea for this does not come from Shor, but comes from Love Grover. So Grover has a search algorithm, which was also being described by Sushmita, that it can search over all possible keys using Grover's search algorithm, basic brute force searching of keys. But search algorithm is optimized by Grover in a quantum domain so that the runtime is improved quadratically. So instead of n, we now have order of root n. That means if I am running AES 128, which has a 128-bit key, instead of running it for 2 to the power 128 iterations, it goes down to 2 to the power 64 iterations. And on top of that, we can use some other information like side channel attack, side channel knowledge, and so on to reduce the search space further. So this is another hotbed of activities in the quantum cryptanalysis, where people are trying to break public key and private key cryptographies by extending the algorithmic and capability of quantum computers. So although it can be noted that in the classical world of cryptanalysis, it's also possible to break AES 128 in considerably less security. The security is 85-bit if I use time memory data trade-off attack, but not as good as 64-bit security, like in the case of Grover's search algorithm. So if I put all these things together, there was a very nice summary study that was presented in 2019 by a group of researchers coming together for a national quantum computing progress and initiatives in the US. This number is a bit outdated, but still it's representative enough that shows if I'm going for the private key or symmetric key encryption, then the time to break this crypto system is still way out of quantum computers. It's still like in the terms of millions of years. Whereas for RSA and discrete logarithmic, it could be within a few hours if we have a big enough quantum computer. That means millions of qubits and large enough gates. So this is where we are in terms of the threat. Now, in order to battle the threat, there was a big initiative which is ongoing and in the last phase of standardization, that's called post-quantum cryptography. So security researchers are coming up with new crypto algorithms. Yes, sir.
Moving to previous point, the mapping of logical qubit to physical, why it experts so high? Like,
So this is the logical to physical qubit ratio. Yes. So this is what Sushmita was also presenting in the quantum error correction domain, that we need to encode one logical qubit by using a lot of physical qubits so that if there is an error that we can recover. So this ratio can vary from technology to technology, but in general, you can take it to be like in thousands. You want to add something? Okay. So this is something, a technological challenge that could be reduced by some other technologies, but still realistically, we can't get it very close. So what I was saying is the post-quantum cryptography is a range of new ciphers in the public key domain that the security researchers are proposing, which can resist a quantum attack. That means we don't have an efficient quantum algorithm to break the post-quantum cryptographic ciphers like we can break RSA or ECC. And this is called for a standardization. So in very near future, like already it's rolling out, there is, for example, a version of Mozilla Thunderbird, which is enabled with post-quantum cryptography. So people are migrating from RSA and ECC to the post-quantum cryptographic algorithms. So one might say, okay, we don't have a quantum computer yet to break RSA and ECC. So why start the migration? The thing is, we may use a lot of classical cryptographic techniques to encrypt data right now. And if there is a determined adversary, if someone really wants to attack, they can store the encrypted data at this point, which will be broken in 10 years from now. So whatever sensitive data that we are encrypting with RSA or ECC, they can just keep on storing it because they know they will be able to break it in 10 years' time. And it still becomes very relevant for them. If it is highly sensitive, then you should start migrating. And it will become standard, it will become mandatory, and next few years you will see a lot of activities in the world of this crypto migration. This happens once a while, like we had a migration from DES to AES at some point of time, because DES was shown to be vulnerable. Similarly, we will have the migration from RSA ECC to post-quantum cryptographic candidates. And this also becomes one of the high point of quantum computing research. So in our lifetime, we will see one point of time where a quantum computer will be big enough to break RSA and ECC, and that will be an event. So we are preparing for that. So this is the timeline of post-quantum cryptography. This was NIST's call for standards in 2016. The first standards are already selected last year, and we are hopeful about the adoption in the next few years. So this is happening in parallel with the growth of quantum computers. So we are getting bigger quantum computers, we are getting more efficient algorithms to break RSA-CC, and at the same time we are adopting new cryptographic standards so that we don't remain vulnerable. So there is another story about quantum cryptography, which many people do refer as quantum key distribution as well. So instead of using a quantum computer to perform some kind of key exchange or perform any encryption, you can also use something like a optical transmitter and optical receiver to set up a secret key between a sender and receiver. So this is, in short, this is called quantum key distribution, or QKD. And one of the earliest and well-known protocol of quantum key distribution is BB84.
Sir, is Diffie-Hellman is also breakable?
Sorry?
Diffie-Hellman is also breakable.
Yeah.
It's also breakable.
Yeah. So in the world of quantum key distribution, the only difference from the public key or post-quantum cryptography is it requires a new kind of infrastructure. So there are lots of spin-offs and government initiatives also, which is setting up the quantum key distribution. Most notably, there is an effort from China which set up a ground-to-satellite quantum key distribution, that they could share the secret key between these regions. But all this requires an effort to set up new infrastructure, new sender, receiver. On the other hand, if you are going for post-quantum cryptography, it can still work on the existing telecom infrastructure. You just need to replace RSA-CC with the new ones. So I'll just highlight some of the recent results that we did on quantum-enabled attacks. And these are, again, divided into two parts. One is on the public key cryptography, another is on the private key cryptography. So this is Neil Koblitz, who is one of the, or the designer of elliptic curve cryptography, and this is Peter Shor. So you can apply Shor on elliptic curve cryptography. And there are a lot of developments in very recent times, because we know that quantum computer is gaining in its capability. So there are works in starting from 2017 and very recently, where there are cryptanalysis advances on different kind of elliptic curves, prime elliptic curves, binary elliptic curves. And I will just highlight some results from this, that you can take a particular curve and corresponding to that, the number of qubits that you need to break the discrete logarithm on that particular curve. As you can see, it's actually reducing over time. So this is the advance that people are making by either designing more clever algorithms or better quantum circuits. So they can reduce the depth of the circuit as well, like it was 2 to the power 32 gates that you need in a circuit to break ECC. Now it goes down to 2 to the power 21. It's still staggeringly high, but there is a lot of research happening on that. And we know once the quantum computer goes in the ability and the algorithm goes in its power, they will meet at some point of time when you will be able to break it. So this is just a highlight of this. I will skip the details because this is the elliptic curve on how it works. So this is the circuit description, which starts with the Hadamard gate. We go into the superposition, and finally we do the measurement after the quantum Fourier transform. So this is the most time-consuming part of the circuit, which goes for the modular exponentiation. And we can do a lot of improvement on the modular exponentiation in order to get more efficient circuit structures. So squaring is basically very simple. The multiplication, which can be done repeatedly, as well as inversion, that is what we want to improve. So if I go for the discrete logarithm, then it will be the multiplication with modular part, and for the factoring, it's a plain modular exponentiation. So this is also a very interesting point to be highlighted here, that we know a lot of arithmetic circuits from the classical world. That we know multiplication, exponentiation, modular exponentiation. If you look back into those classical circuits, and if you can do some improved implementation of those in quantum world, you are directly helping the whole research. And it's not very difficult. So for a lot of people who ask me that, okay, I want to do something in quantum computing, but there is a lot of physics, there is a lot of maths. It's not always like that. You just do a multiplication, okay, how the multiplier is implemented. If you can do an efficient implementation of that using quantum gates, which can resemble a lot of classical logic gates, then you directly improve the results. So this is one of the showcase examples for that. And the other part of the quantum cryptanalysis is to run Grover's algorithm on Rindell. Rindell is basically the AES standard. So this is Ridgman and John Damon. So this is again receiving a lot of attention because people are trying to reduce the complexity of the attack on AES. So over these years, there are many papers appearing in the top journals and conferences where they are trying to get into better circuits for AES. So one of the highlights again here is to look into what kind of basic operators are being used. So there is an Galois field inversion that has to be implemented in the quantum circuit for this. And we know that the squaring and multiplication are also basic circuits. Multiplication is costly. These circuits have been improved and implemented over time. So there are results from the number of gates, the depth and number of qubits that you need in order to break the AES circuit. So this is the full circuit implementation. So this is something that you can actually implement on your own. There are very nice quantum simulators. You can do this simple school book multiplication, but that incurs high cost in the substitution box of AES. But what you can always do is that instead of directly going for the quantum implementation, look into what has been done in the AES in the classical world. You can transport a lot of results from there. So for example, there are very efficient substitution box implementation of AES in the classical world. So what we are doing in the Grover search, we are calling the AES repeatedly. That means the AES as it is needs to be implemented in the quantum circuit. So you can take the efficient implementation from the plain CMOS or classical S box, map it into the quantum gates. So this is some results that we have been working on, and what we could show is that the AES quantum circuit, the security that one claims for different levels of AES, there's a level 1, 3, 5, depending on how many bits of key size that you are using. Compared to 2 to the power 170, we are able to reduce it to the power 157. So this is still a bit theoretical exercise, because with 2 to the power 157, it's way beyond the reach of any computer. But the claim remains valid because sometimes people go for very simple ciphers, which we call as a lightweight cryptography. And if you say, I'm using an 80-bit key, it may be out of reach for a classical computer, but it will be broken immediately in a quantum computer because you are getting the complexity down to Grover search, which is quadratic. So it will be in 2 to the power 40 order. So to summarize, this is a part of the application presentation. It will be followed by what Amlan has to say about quantum machine learning. What's happening in the quantum world is the quantum computers are getting powerful. And this is the equivalent of Moore's law that Google is promoting. They call it Neven's law. They say, okay, the number of qubits and number of gates that will grow exponentially in the years. So this is also being pursued heavily by IBM and so on. So if they are able to do that, clearly the security protocols are going to be disrupted. That's already noted by security researchers. They are coming up with post-quantum cryptographies and so on. So what we can do is we can prepare for post-quantum security and at the same time assess other options like quantum key distribution, how to make the circuits more efficient and actually break to see this timeline of change. Okay. So now we switch over to Amlan. Yes, yes.
Excuse me, can you hear me?
Yeah, I can hear you.
Yeah, I'm really sorry. I just was wondering. I'm Anuban. This is Robert. I don't want to interrupt. Just as I said, I have to leave in 40 minutes. So I was wondering.
Which one? Sorry, I missed.
Yeah. Yeah, this is Robert.
Yes.
And I said I have
okay,
to
Robert. So there. So you can do it now if you want.
Yeah, I'm really sorry. I don't for that, but because I have to. There are 1,000 students waiting for me. Otherwise.
Okay. Sure. So okay, I will take your question offline. Okay. So yes, sure.
Okay. Can I share my screen? Can you see my screen?
Not yet. Yes, Robert, you can start.
Oh, okay. You can see my slides?
Yes.
Okay, perfect. Then first of all, thanks a lot for having me, and I'm really terribly sorry for squeezing myself into that. It's breaking a little bit the flow of the tutorial, but as said, there are 1,000 students otherwise waiting in half an hour for me to give the lecture. So I hope it doesn't mind. So what I'm trying to do is I'm trying to fit in what I'm going to talk about a little bit into the existing part of the structure. So literally, in my part of the tutorial, I was supposed to talk a little bit about simulating and testing for quantum computing. And this is kind of embedded into the entire tutorial as follows, that we heard already in previous talks by Susmita, by Professor Manan, by Anupam, about that there are several applications for quantum computing. And right now, my talk rightly goes in the middle between Anupam's application talk on cryptography and Amlan's talk, who was supposed to explain a little bit how applications can be realized. So what I'm using a little bit here as motivation is that once you have all these exciting quantum computing applications, what you eventually have to do in order to realize them on an external machine, you have to compile them down to an elementary representation. So in the software side, we would say you have to compile it down. In the hardware side, we would say you have to synthesize it down. Literally, what you have to do is you have your application on a higher level, your conceptual quantum algorithm, then you have to map, and you want to map that on a particular target device. And for this purpose, you have to do something like that. You have to map non-elementary gates, which are not supported by your target device. You have to map that, for example, into a sequence of elementary gates. And then you have to map sort of like all your logical qubits to physical qubits on the device. So you have to, you're working on qubits Q0, Q1, Q2 here, and then you have to map that to some sort of physical qubits Q0, Q1, Q2, Q2. This may cause some dependency in the orders, so you have to do a little bit of that. And then maybe in order to improve all that, you have to optimize that. For example, you have two H gates, which Susmita introduced before, and you can cancel out these H gates. And you have a couple of sequences of gates here as well. And then you can optimize upon that, and you end up with a smaller circuit. So I don't want that you understood all the details of that. That is going to be covered later on. But the main message of this particular slide here is that you have at the beginning your original quantum computing algorithm, and in order to execute them on a real target device, you have to synthesize or compile that through different abstraction levels. And this is a huge part of any quantum computing flow. And in my talk, or my part of this tutorial here, I want to discuss the thing, once you have done it, how do you make sure that what you have inserted at the top of the flow is still, and what you compile down, that how can you make sure that what you generated at the end of this compilation flow is still functional equivalent to what you have inserted before. That's a typical verification problem, a correctness problem, happens in the conventional realm as well. If you have a conventional program or conventional hardware, once you have synthesized the circuit, or the circuit, or you have compiled the software program, you still want to make sure that your compiled program or your synthesized circuit still realizes the same functionality than the original one. And this is actually what I wanted to cover in this particular thing here. I want to address the questions, how can we make sure that your compiled result is still correct? And for this, as the title of my part suggests, we have two methods, simulation and formal verification. And both methods I would like to briefly sketch here. And I want to make a point a little bit that could be really interesting. I want to make an assumption that maybe, although lots of the design steps in quantum computing are harder than the conventional computing, maybe quantum computing is a case where verification of a quantum circuit could be easier than the verification of a classical circuit. So this is a little bit the assumption I want to make. I'm not clarifying this assumption in this talk entirely, but I want to make a little bit, discuss that a little bit. So long story short, what is this? What is my part about? I want to address the questions, is the compiled circuit correct with simulation and with formal verification? And this is said very similar to the conventional realm where we have the similar problem as well. Now I'm just discussing that through with quantum circuit. And the first thing is that, in fact, a very naive thing, how you can check whether or not your compiled result is correct, is you just use simulation. What does it mean exactly? You have your two circuits. Let's say this is our original circuit here, and this is our compiled circuit. One thing you can easily do is you can simply randomly generate some sort of an input pattern, a basic state. You apply this basic states to both circuits, and then you simulate those circuits. That means but you check out what kind of output state is generated if you give this particular input state to both circuits. And then you've got two output states, and if these output states are equivalent, it means if their fidelity is equivalent, then if this is the case, then you have checked that those two circuits are correct, but only for the single basic states. So technically what you have to do is you now should determine another basic states and repeat that. And of course, this is a very naive solution, a solution which is infeasible in the conventional realm, because usually when you do that, you have to check out all possible input patterns, all possible input stimuli. And usually in the conventional realm, this amounts to 2 to the power of n, n being the number of input signals, possibilities. Obviously here in quantum computing, we have a similar complexity. If you can focus on basic states, you have the same number of patterns. So in general, this is a solution which could be nice to validate maybe something, but certainly not to verify something. But let me bear with this, because this is something that's usually what we do very often. We compile something and then we just execute it with some sort of test patterns and test scenarios, checking out whether or not it's correct, although it does not give you a guarantee. Because in order to have 100% completeness, you would need to do this for every single pattern. However, once you get a pattern where in which you apply to both circuits and those output patterns are different, so assuming you generated a pattern, you simulated both circuits with this pattern, and you've got different outputs, then you can conclude that obviously you have a counterexample. Obviously, those two circuits are not functional equivalent, because for the same input pattern, you got different output patterns. So this could be some sort of a very naive flow in which you check out all possible basic states. And if you find someone where a basic states as input leads to different output states, then you have proven that your two circuits are not correct. This now raises the questions, how likely is this? And as said, in the conventional realm, this is an infeasible technology because in most of the cases, it was very hard that even if two circuits are not equivalent, it was very hard to determine input stimuli which show this equivalence. We had all those formal methods, model and checking methods for that, because it was very unlikely that by just randomly generating an input pattern, you can determine an error in both circuits. However, in quantum computing, Susmita was mentioning before, in quantum computing, everything is reversible, which makes it much harder to mask errors in a circuit. As a good example, if you consider an AND gate, from the conventional realm, if one of the inputs of the AND gate is a 0, the output automatically is 0. That means even if the other input might be affected by an error, it will be masked. Now, these masking effects also exist for quantum computing and also for reversible computing, but not as drastically. And in fact, we observed in several evaluations that many errors actually propagate through, or that even slight changes in a circuit actually affect the entire functionality. That means what I'm trying to say here, if you have two quantum circuits and they just differ in very slight aspects, maybe a removed gate or so, then there's a decent chance that the functionality is so heavily affected by that with just some randomly generated input stimuli, you can actually determine that. And in order to explore that, we tried a couple of case studies on that. And for this, we used several simulation methods. So simulation itself for quantum circuits is a hard problem on its own, but several solutions exist, several tools exist. I'm just listing here a couple of papers which cover this particular topic. And once also all these platforms which have been mentioned before, IBM Qiskit, Microsoft's Google's Circuit, and so on, they all offer simulation methods. So what you can easily do is you can take these methods, consider a couple of benchmark with two circuits, one original circuit, and one compiled circuit, for example. And if you then try to simulate them exhaustively, you get sort of like these runtimes. So this is kind of an equivalence checking method, which the runtimes of an equivalence checking method, which tries to prove everything 100% complete. And now what we did here is, we just simulated 16 input patterns with the simulators I mentioned before. And you can see that this is the first message I want to convey here, that you can see, although simulation of quantum circuits per se is complex, it is not as complex as formal verification. So the runtime of a formal verification scheme is much higher than the runtime of just simulating 16 patterns. So the first message I want to convey here is that simulation, if you want to use simulation in order to check the correctness of your circuits, the corresponding runtime is only negligible, or the overhead is negligible. So simulation does not cost you a lot. The question, of course, though, is, does it detect errors very nicely? And in fact, it does. So this is another set of experiments. Again, we have circuits and we have compiled circuits, and then we injected errors into the compiled circuits. And then in this column here, we evaluated how many simulation patterns do I need in order to detect these errors. And this is one of the messages why I would like to make the point that quantum computing might be a better case for verification, because due to the reversibility I was mentioning before, just very few patterns, this is the number of patterns I needed to simulate until I get a pattern which shows the non-equivalence. And then you can see for many instances, just a single pattern, or maybe 4 pattern, maybe 11 pattern, which have been simulated in a fraction of a second, only few patterns are sufficient in order to detect the error in a quantum circuit. Of course, again, it's not complete. We have this example here, for example. I simulated a total of 16 patterns, and none of these patterns showed the error. So it's not guaranteed, but, and that's the second message here, there's a magnitude of improvement in case there is non-equivalence. So that means if I have an error in my circuit, few patterns in many cases already will show the error. And then last but not least, what we did as well, we checked a little bit, again, 2 circuits, and then in one compiled circuit, we removed 1 gate, and another we removed 3 gates. So we increased a little bit the error and make the error a little bit more drastical. And then you can see Already in when I just have a slight error, I get, this is the kind of with how many simulation runs do I need in order to detect the error? And when I just have a small error, I can already detect the error in 80% of the cases. If I have a bigger error introduced, removing 3 random gates, then I can detect the error in almost 100% of the cases. There are a couple of things. So what I want to make here is that the main message here is that even slight changes can be detected just by simulation. And this is kind of the first big message I want to do. If you want to check whether or not your quantum circuits are correct or not, simulation, a technique which hasn't been really used for verification in the conventional realm, at least not when you're aiming for 100% completeness, simulation can be much, much, much more powerful in quantum computing than it could be in conventional systems. So simulation really could make a difference. However, a big problem remains: simulation never can be complete. If I simulate just 16 patterns, there is, as we've seen here, there is always the chance that I cannot detect a particular error. So if I want to be really 100% correct, I have to do some sort of formal verification, some sort of formal method. And conceptually, this is also very easy, because what is equivalence checking defined as? Again, you have 2 circuits, the left-hand circuit, the right-hand circuit, the compiled circuit, and you want to know whether or not they realize the same functionality. So what you can do is, conceptually, you just take all the unitary matrices representing the functionality of this gate. This is these matrices here. You multiply them together, and then you get the overall unitary matrix of the overall circuit. And then in a similar fashion, you can do this now with the compiled circuit. You take all the single unitary matrices of those gates here, multiply them together, get the overall matrix, and now you have a functional description of your left-hand circuit, a functional description of your right-hand circuit, and now you just have to make sure if both functional descriptions are equivalent. The problem, again, very similar to the conventional realm. In the conventional realm, we're doing the same. You have one circuit, you can generate a truth table of this one circuit, and you have another circuit, you generate a truth table of this other circuit as well. You compare the truth tables. But of course, the main problem is that those truth tables grow exponentially in the number of inputs. So these, in the same we have here, these unitary matrices, they grow exponentially, though they look like something like that. They are 2 to the power of n. I'm sorry, they are they are unitary matrices of the size 2 to the power of n times 2 to the power of n. So we have a huge problem here. However, again, as in the conventional realm, certain data structures exist which allow to represent that in a very efficient fashion. One of these data structures could be ZX diagrams, which have been very heavily applied in quantum computing. Tensor networks are used, or in particular, in our group, we're using a lot of decision diagrams. Decision diagrams are a data structure which allowed in the conventional realm to represent Boolean functionality, literally truth tables, in a more compact fashion, trying to overcome this exponential overhead. And without getting in too much detail, just by sketching it here, we don't have the time for details, but sort of like we can do something very similar. We can apply decision diagrams also to represent unitary matrices. So the unitary matrix you see here on the left-hand side can be represented in terms of a decision diagram you can see on the right-hand side. Unfortunately, due to time limitations, I don't have time to dig deeper into that, but you can take these decision diagrams as a black box, just accepting that this here on the right-hand side somehow represents our unitary matrix here at the left-hand side. And then the sweet thing is that these decision diagrams, again, I'm copying conventional ideas from the conventional realm. Those decision diagrams are canonic. So what you can do is you can generate a decision diagram representing the functionality of this left-hand circuit. You can generate the decision diagram representing the functionality of this right-hand circuit. And if both are actually functional equivalent, so must be then the unitary matrices have to be functional equivalent. And the decision diagram is a canonical representation. That means, as you can see, both decision diagrams are equivalent. In the real implementation, they would even share this memory. So literally, this is our decision diagram where this pointer G represents to the decision diagram representing the functionality of this circuit. This G prime represents the functionality of this circuit. And since both pointing to the same place, we can conclude both circuits are equivalent. So long story short is what you can do is you can just take decision diagrams out of the box or off the shelf, generating, throwing your quantum circuit in there, and then comparing whether or not two quantum circuits are equivalent. The fun thing, however, is we can actually do even more than that, because right now, as said, Susmita was mentioning that, emphasizing that a lot. Everything in quantum computing is reversible, and because of that, we can employ this particular scheme here. That means if you have two circuits, G and G prime, then you can take the inverse of one circuit, multiply it with the other circuit, and if both circuits are equivalent, then you should end up with the identity. And this is something very exciting, because what you could do is you can take your two circuits, then you can inverse one of these circuits, which is easy because everything in quantum computing is reversible. So let's inverse this circuit. And then when you now multiply all that together, you should get the identity. And the identity is good because using the decision diagrams from before, but also with ZX and the other data structures, the identity is a functionality which can be very efficiently represented. So this is the functional representation of the identity, which is linear in space. So identity is really what we like. And in the first glance, what this shows a little bit like, okay, checking this verification problem is easy because eventually my result is linear of size. So this sounds very promising. The small problem, though, might be in order to generate this matrix, I have to multiply all these unitary matrices together. That means in the worst case, once I multiplied all those first gates here, I still may end up with a large circuit, and I only get back to the identity by multiplying the remaining circuits. So this might be still a little bit the roadblock, but the potential is there. And how can we use this potential? Well, we're using that by not multiplying all the gates from the left to the right until I reach the identity, which may lead to these bigger intermediate results. But what we could do is we could start at the identity itself. And then we could think about, okay, now I multiply, let's say, one gate from the right-hand circuit. I multiply this gate on top of my decision diagram. And then I multiply a gate from the other circuit, and then I get back to the identity. And now the point is, if I do this in a very clever fashion, multiplying a couple of gates from the right-hand side, then multiplying another gate from the left-hand side, and so on. If I do this with the clever structure, for example, if I know this gate here, which I just multiplied to my decision diagram, now is covered by all those gates here on the left-hand side, I can come up with some very interesting schemes, which in the end still yield my identity, proving that both circuits are functional equivalent, but at the same time trying to stay always as close to the identity, which does not cause the exponential overhead. And this is a couple of strategies what has been developed, and which, in fact, if we're using this clever, can be used in order, in the best case, if you have a perfect oracle telling you when to apply gates from one circuit or the other, you can end up with an formal verification scheme which remains linear in complexity. And the only question then, of course, is what kind of strategy should we apply? Can we exploit knowledge about the relation between two circuits? Because we know those circuits realize the same functionality. They have been created to a computational flow. Can we utilize that? And what kind of efficient method result on that? And again, just sketching that, you definitely can take your compilation flow and get some ideas how to apply these gates, because you know that this gate has been mapped to this gate. You know that you have mapped some qubits to other qubits, that the order of qubits changed, and you know that maybe you applied some optimization schemes. So you can use this compilation, this information from the compilation flow, and incorporate it into your verification scheme, and then you will be able to do the verification just and at the same time, if everything works out beautifully in just linear complexity. Doesn't mean it always works like that, but in contrast to conventional computing, where you often have to tackle exponential complexity, there is a lot of potential, and that's what I brought up in the beginning. There's a lot of potential how to make verification of quantum computing easier than maybe verification of the conventional one. when you want to play with that, we have everything on that. What I just described is publicly available in open source implementations. Here's the corresponding links. Maybe the slides will be distributed to you, all of you, then you can check that out later. Everything is implemented. If you don't want to, install some sort of software, we even have a web page which includes a web-based GUI where you can play around. You can load a quantum algorithm into this web page, and then you can play around a little bit how to simulate this quantum circuits, how to verify this quantum circuit. So you can play around with that, hopefully with a low entry barrier. Overall, and this is the main message what I want to convey, this may lead to a verification flow which could look as follows: that you have your two circuits. You first just try out simulation. That means you randomly simulate a couple of patterns. If they always lead to the same result, if they lead to different results, then you already can conclude these two circuits are not equivalent. Then you can already use simulation very efficiently to check out your two circuits are not equivalent. If this is not the case, then you set yourself a threshold how many randomly or maybe dedicatedly generated stimuli you want to generate. So you decide how often you want to do simulation. And if you reach the point that you said, okay, you simulated enough, this doesn't show any kind of problems, already this alone gives you an indication that most likely your two circuits might be equivalent. But if you want to be sure, then you use formal verification, and then you can use these decision diagram-based methods, which I sketched before. And if they show both circuits are not correct, then you have formally, then you get an counterexample. If they show both are formally correct, then you have a 100% guarantee that both circuits are realizing the same function. And even if you still run into complexity problems here, that means even if you end up with some sort of timeout, you don't have a 100% proof, but as mentioned before, due to the power of simulation and to the fact that due to everything is reversible, errors can easily be detected. Even if you weren't able to verify that because of complexity reasons, you may have at least an indication that your two circuits most likely are equivalent. It's no guarantee, but in contrast again to the conventional realm, this is still a better thing, a better kind of conclusion than you have in the this is a strong conclusion than you could have in the conventional realm. So sorry for rushing through, but what are the take-home messages? First, as sketched at the beginning of my part, in order to check the correctness of your circuits, simulation can be very powerful. In contrast to conventional realms, you have an AND gate in a conventional circuit, and it masks away a lot of errors. In quantum computing, many errors cannot be masked. This is already very powerful. Then you can utilize information on the compilation flow, as I just said before. And when you combine simulation and verification, you get this sort of overall integrated flow, which either shows the two circuits are not equivalent, it proves that they're not equivalent, and even if you still suffer from complexity, you still get a better kind of indication than in the conventional realm, where you often have no indication. So those are my take-home messages. Again, terribly sorry that I sort of broke up a little bit the flow. What else, again, the main message here is that once you have all these great applications my predecessors talked about, and once you compile it down, in order to make sure that they are correct, you can use simulation and verification methods. And maybe, and I hope I gave a little bit of ideas here, maybe even this part, checking to correctness, is easier in the quantum computing realm than it is in the conventional realm, which in my opinion is a cool thing, because most of the time everything is more complex in quantum computing than in conventional computing. So it might be a nice difference that maybe for this particular problem we can exploit actually something from quantum computing. With this, thanks again for having me. Sorry for blowing up a little bit the schedule. I hope still some ideas came through. Thanks a lot.
Yeah, thank you, Robert. Yeah. So any questions from the audience for Robert? Okay. So Robert, I think if there will be questions, we will push it to through mail so that you can get back
Absolutely.
to the participants. Okay. Yeah.
Thank you again, and sorry again.
Thank you, Robert. Yeah, thank you, Robert, once again.
Bye-bye.
Yeah. Yeah. So I know that we are running out of time, so I will just try to quickly yeah, I finished my lecture on this. Yeah, I need a display. Yeah. Okay. So what I will be presenting will be on the quantum optimization. Okay, some of the algorithms of quantum optimization and okay, how we can approach towards quantum machine learning. There are a lot. Okay, you need to stop. Okay, okay. So Robert, you need to stop from your end. Stop your presentation. Yeah, this is already there. But he needs to. Okay, it's there, right? Yeah, this one. Yeah. Yeah, fine. So let me move like this, right? Okay. Okay. So my today's lecture agenda will be some of the optimization techniques like HHL, the quantum approximate optimization, the solving satisfiability problem with Grovers, and quantum and a bit of that, and then some of the very basics of quantum machine learning. Maybe that means, yeah, so if I have maybe 10 or 15 minutes time, I will be just skipping some of them, okay. So what we do here in the quantum algorithms, as already stated by Shushmita Di, that we start with some qubits and we actually have some manipulations of the qubits over the quantum gates, right? And then we do the measurement, which is here. So what we actually do, we actually start with the initial probability distribution of the states, which may be all they are on the same probability domain, and then we try to. So the actual cost of quantum algorithm is how we can start with this initial distribution of the quantum states, which are all equiprobable in the most general setting, right? And come up with a probability distribution which prefers the result state, right? And that is entirely the game of quantum algorithm. Okay, so when you look into this, how we expand the problem, that is how the quantum algorithm helps. It expands the P class of problem, okay, to the QP class of problem, and it gets into the NP space, which means that provided we can support an error which is called a bounded error quantum polynomial. So if we can actually, okay, it perceives some amount of error, we can actually solve some MP problem into the polynomial problem in the quantum domain. But having said that, it is not always true that all the algorithms can be reduced to BQP, right? So we have to test the algorithms which are in BQP, and that's the call, okay, where we do the quantum analysis of the problems, and then we design the problems and implement them, okay? So first I discuss this HHL algorithm, which is a very basic algorithm, and that is used for a lot of the machine learning or optimization activities, like when we do the linear regression or we do the support vector machine. We have to solve a function something like this, where A is known to me, B is known to me, but we have to find an X which actually operated on X results to B. So we have to evaluate the X. So how we start with this, we have the vector representation or the matrix representation. There are some assumptions of A. So A we actually consider as a vector which has an eigenvalue, and this is an invertible vector, invertible matrix. Okay, so this A operates on the state. So we know A and B, and we have to do the A inverse B operation to get the X. Okay, and it is always guaranteed. So the matrix A will be such that it is guaranteed that it will be having an A inverse. So as it will be having an A inverse, we can actually convert it to a unitary transform, right? And we can actually do the quantum mapping of this particular problem, right? And that is the solution what was proposed by Harrow, Hasseltine, and Lloyd in 2009. Right, and these are the conditions what we have to do. We have to have the two eigenvalues of A, which is lambda max and lambda mean, right? And there is a thing that it should be not too big. The ratio should only be big. Okay, it shouldn't be a very widespread. Okay, matrix in terms of of the eigenvalue distribution. Right, and obviously there's a unitary operation e to the power ia, which is a conversion of the Hamiltonian. We will use the Hamiltonian operation to represent this particular function, right? And that is also sparseness, which means that a has that means up to a certain number of non-zero values. Okay, it is mostly sparse, right? These are the assumptions which make this algorithm better in the quantum setting. Okay, so how we start with the basic algorithm here is actually the quantum phase estimation, which is also one of the key component of the Shor's algorithm. So what we try to do here is that we will try to assume that there are some eigen values and eigenvectors of the matrix A that is represented by lambda 1 and V. Okay, V are the eigenvectors and lambdas are the eigenvalues. Okay, similarly, what we do here, we actually try to represent the state B also, okay, right, in our quantum encoding. So this is the quantum encoding of the state B. Okay, so B, this is very simple. We can do our initial superposition of all, initial superpositions, and then we can project the superpositions on the probable values of the B with a unitary transform, and we can encode the state B in this particular form. Right, and then comes that is how we can generate this particular a to the power -1 or the inverse of a, which we multiply by this b and will generate the x. Okay, so this eigenvalue estimation is basically a process called quantum phase estimation, which is not being explained in details here. Okay, this is the way by which we can actually use say operator something like e to the power minus ah of the form, and we can actually try to find out that what h actually converts this particular matrix to the equivalent of vi lambda I. So lambda I are the eigen values of the A. So we try to represent the matrix A in the superposition of eigenvalues of A. Right, and then we take an extra ancillary qubit, right? And this ancillary qubit defines a sort of distribution, right? The distribution is two parts. One part is lambda. This is the inverse eigenfunction of A, right? And this is the other part of it, right? So what we have to do, we have to actually take this particular component out, and we have to do a measurement so that we can get this component out, and we can measure what is lambda I -1, which is the inverse of the matrix A, right? And then we can actually get back this X operating on the vector B, and because VI's are the representation of the vector B. So this is the way this we can do, because there are two principal things we have to do. We have to do a quantum phase estimation, which actually works here, right? And there is a superposition of states in the ancillary qubit, right? And then with a suitable sort of measurement operation, which is called an inversion of the phase estimation once again. With a suitable operation, we can come back to this particular setting, and then we can do a measurement which can approximate, which can approximate the eigenvalues of lambda of the vector A, right? And we can generate the value of X. Then we will. So this is the next algorithm, which is called quantum approximate optimization. We try to solve the approximate problems. So here, what we try to do, we try to start with this uses a particular technique called quantum annealing. Okay. So as Dr. Manoj said in his, if you see his first presentation, he said that there are two types of process. One is the quantum gate process, and one is the quantum annealing process. So this uses the concept of quantum annealing. So what it tries to do, it tries to start with a Hamiltonian, which is a particular down state, right, and tries to reach to a Hamiltonian, which is the ground state of the solution. So the solution represents the ground state of a Hamiltonian, right? And you don't know that what Hamiltonian you are currently. You have to initiate your system to some Hamiltonian, right? And then with some transformation, you have to reach to the ground state of your target Hamiltonian, right? And probably the target Hamiltonian will give you the solution of your optimization problem in an approximate way. Okay, because it's not always guaranteed that you will reach the exact ground state of your target Hamiltonian. Okay, so this is a movement, okay, from a Hamiltonian maybe HP, okay, to a cost Hamiltonian HC and to its ground state, okay, with some transformation. And what we can do in the transformation is that, okay, this is the transformation. So if you look into the problem, we start with an operation U beta gamma. U beta gamma is a generic unitary operator, right? Which will transform the Hamiltonian from this to this, okay? From your certain Hamiltonian okay, to the ground state of your cost Hamiltonian, right? And how you achieve this U beta gamma? This is a slow process. This is called a Trotter decomposition. So using a Trotter decomposition, you can actually split a gate into a series of e to the power minus a HT form, right? And this H can be a summation of H1, H2, H3, H4, something like that. So you try to approximate this, okay, this particular operation, right? This particular, okay, psi beta gamma, which is a result state, right, is an operation consisting of a sequence of U beta U gamma on some initial state, right? And this is possible in the quantum domain, okay? And then there is another question that how can a Hamiltonian can become, okay, how can a U beta, okay, can be converted to an equivalent Hamiltonian? This is a decomposition technique where we can actually represent a Hamiltonian using a sequence of unitary gate operations, right? So a U beta, right? A U beta can be presented as a sequence of gate operations which defines the Hamiltonian, right? And this can be realized in the quantum domain. Okay. So now actually we have to realize these operations, right? Though mathematically represent these terms, but actually we have to do these operations in the quantum domain. Okay. So this is a sequence of operations which will actually lead to the optimum value of beta and gamma. And this beta and gamma will actually go to the result, desired ground state, right, which is the optimum state of your system or your solution, right? So how we try to do this is this also have a very simple notion. Okay, so the notion is that if you have to come to H alpha, right? H alpha can be a decomposition of HS and HC. Okay, so your HC may be the okay. So HS is a simple ground state. Okay, the initial ground state, right? And HC is the ground state where we want to reach, right? It gives you the minimum cost. Okay, that means optimization of your function. Okay, optimized value of your function. So we have to start with HS and we have to reach to HC. So what we do that we start with a state which is a mix of HS and HC, represented by 1 minus alpha and alpha, the coefficients of corresponding HS and HC. So if we can slowly make this alpha 0, right, then we actually come to HS. But if we can make alpha equals to 1, then this H will be converted to the HC, which is the ground state of your Hamiltonian, right? And the entire game of this quantum transformation is actually how we can modify alpha so that I can set ultimately alpha nearly to 1, and then your Hamiltonian will converge to a very near approximation of HC. Okay, we tell it's an approximation due to this reason because it is not obvious that alpha will be made exactly 1 and we can make one component exactly 1 and another 0. So when we measure the system, it will be a very high probability of HC, right, and corresponding to HS, and we can tell its approximate solution. So there are circuits by which we can implement this. Right, this all operations are rotation operations, and there are some combined operations which are the continuous operations which can actually entangle some qubits, right? And we can generate some sequence of this U to the power this U beta gamma operations, right? right? And we can do that. But the way we adjust this beta gamma can be a classical help. This is normally practiced. So the way we try to adjust beta gamma is this process. We try to prepare with initial values of beta gamma, and we try to do a measurement of the expectation value. We see whether the Hamiltonian reaches the ground state. If not, we try to again modify with a classical function. We try to work on this beta gamma. We try to optimize the beta gamma, right, and try to reduce that so that it can come to this particular HC faster. Okay. So this takes a classical handle which can actually make this quantum optimizer work faster. The other algorithms which are also there, which is the Grover SAT problem. SAT problem is that means it can look a little bit simple in the quantum setting. So we have a satisfiability problem represented by this Boolean expression. This is a three-SAT problem because this has three variables, and we can actually list the solution which are actually which gives you the true values. So the solutions are those which gives you the true values. Okay, so we have to do a sort of encoding process so that we can test an input, right, and the corresponding input will result to true or false. We can encode this with the quantum circuit. Okay, so this particular so these are the process by which we can design the quantum circuits, which are basically consist of some sort of combination, C0 operations on multi-control Toffoli gates, right, which actually tries to implement this Boolean function and tries to set a particular. These are all ancillary variables. See, these zeros are ancillary variables, right? And each of the ancillary variables will be set or reset depending on the partial satisfaction of all of these sub functions of the entire SAT problem. Okay, right? And ultimately, we can set a particular result. Bit or ancillary bit, which if all these are true, right, then this particular result bit will be set. Okay, right, and using this type of formulation, we can actually represent the SAT problem in your quantum circuit, right, and you can try to work on that. So there are ways. This is the HICC example how we can take our data. This is a representation of your Boolean function, right? And there's a particular format called DIMUS format for your HICC, and you can represent it as a data file. Suppose you push it the data file of a satisfiability function, it will generate a particular circuit. It has its internal module. It will generate a particular circuit, and then it will try to maximize those states which results to true. So these experiments you can just try out for using that HICC platform. This I will not discuss a bit. This is one of the problems we have solved very recently, which is basically based on a mixture of reverse search. Okay, it is basically a mixture of reverse search and some intelligent preparation of the initial state. This is an equivalent of the quantum AND. So quantum AND is two functions, which is actually it tries to propagate in every path using the superposition principle, right? And then there is a pheromone deposition and pheromone annihilation, which is actually which is increasing the weights in certain paths and again decreasing the weights in certain paths. That is done in terms of interference in the quantum domain. We have the constructive interference and destructive interference. We actually use the suitable operators which can do that in specific path, and then we do a Grover search to find that which particular path gives me the best cost. Okay, and this is the way we have formulated this algorithm. I'm not getting into details of this, but these are also the ways that, apart from the specific tracks like QAOA, like HHL, right, satisfied problem. We can also so use the tools like Grover and interference and superposition, and you can also come up with some solutions of some problems. Okay, so now I will so I end optimization problem here, and now I will give a very brief overview of how we can move into the quantum machine learning. So as we know, the machine learning is basically an hypothesis where we try to use the data and we try to generate an outcome out of a hypothesis, and probably the outcome gives you gives you the good outcome for majority of your training set. You are very satisfied that this will work for your test data also. Okay, this is the basic assumption of machine learning problem. Because when we cannot represent something in a mathematical form, or the mathematical form is pretty hard, then we try to use a hypothesis form, and then try to use the data to mature this hypothesis, which becomes a learned model, right? And the model works in the next process. So now what we try to do, we have seen that there is a tremendous progress, or that means, or I will say there's a tremendous push. I don't know how much is the exact progress in terms of the outcomes, but there is tremendous push, promise, hype, whatever we can tell, right, on exploiting the machine learning in the quantum domain, right? And every big giants are working on in some aspect of this quantum machine learning and trying to develop the quantum architecture and the quantum tools, so that the quantum machine learning can be very well demonstrated on the platforms, right? So now the basic, one of the way of looking into the neural network model, what we normally do in the machine learning is basically how we can adjust the weights, right? How we can come from an input vector to an output vector, and we have a combination of the weights. The weights combines with the input vector and does some sort of transformation of the input vectors in the different layers, and tries to come to an output vector, which is your solution, right? So similarly, we can actually do the transformation of the quantum state. So a quantum circuit can be visualized something like this. Okay, what we discussed in this entire tutorial, it can be thought like something like this. We have the initialization of some qubits in some states. Okay, states may be all 0, all 1, or maybe superposition of zeros and 1, whatever is the state. Then we have some parameterized quantum circuits. That means, I think Professor Sushmita has already said that you have the U theta, the theta form, the R theta, the RX theta form of circuits. So those theta are actually the controlling operators, which actually define what transformations you are doing from the qubit space. Okay, staying in the qubit space. So the qubit registers, which are initialized, goes through a continuous evaluation with this particular theta values of the gates, right? And then we come to a particular state of the qubit register, where we can do a measurement, right? And we can come to our output vector. Okay? So the entire assumption can be that how we can very well choose the parameters so that we can define exactly the U theta. So U theta can be defined as a single block. They're defined as a single block logically here, right? It will be a decomposition. The decomposition may be multiple qubits operating on the multiple gates operating on multiple qubits, or maybe multiple gates operating on the single qubit, or a combination of both. Okay, so if you look into this, I'll just skip a bit. So these are the combinations that we can do, and this is called the answers. This is the way of representing that how we can decompose a parameterized quantum circuit into the component quantum operations or gates, whatever we tell, right, in terms of the parameterized forms. Okay, so the parameterized forms will be, this is one of the way, and then there will be a combination of this, and there may be entanglement, or there may be a combination of multiple qubits, right? So this is the way how you have to generate the U theta corresponding, right? And these thetas are your learning parameters or the hyperparameters of your model, right? We know in machine learning we tell what are the hyperparameters of a model, what parameters you have to tune, right? And we have to supply to your network. Okay. So this is the form how which you can develop your quantum learning, quantum circuit for machine learning, and you can tell that your circuit is learned, provided you can reduce the error for these measurements of theta values. Okay, and there are a lot of activities out there. QML itself can be as we know that there are quantum simulations which can use the QML. There are itself some problems in the quantum domain itself which can be solved by machine learning. Actually, myself and Sushmita is working in some of the problems in that domain, using how we can use the machine learning to sort out the errors in the quantum circuit. So quantum machine learning can be itself used for improving quantum circuits. Okay, Then there are some important applications in image or in text, which requires the machine perception, and then we can develop the quantum machine perception. Okay, right? And there are some way we can actually do a partial quantum operations for a big classical routine, where we can take certain operations in the classical domain, and we can prove that certain operations can be done better in the quantum domain. So we can have a classical quantum handshake, in this type of applications. So as I said, there may be two verticals here. One may be the classical data, quantum data, and then the classical process and quantum process. So we can have all the sorts of combination. If we are doing purely classical ML, we are here, right? And if we are, and the current quantum domain is something like this, right? But we are steadily moving towards quantum data and quantum machine learning once we have the more and more applications entirely being rolled on the quantum system itself. Okay. So now I will just give a brief overview that as we know that machine learning, I think, it was discussed by Anupam also. That means we try to actually make a non-linear space to a linear space. Okay, in our machine learning problem, and that's called the kernel trick. So using the kernel trick, we map a particular non-linear. That means in a feature space where where it shows non-linearity, right? You can convert or transform the feature space where you can actually very easily partition the data points. Okay, in that particular transform feature space. So we can do a quantum transformation in terms of the feature space. So we can take an input space which is classical, and we can push it to a Hilbert space, right? I have already give you some hint that how we can use the e⁻⁸ operator, right, which defines an Hamiltonian transformation, right? And we can have a lot of ways to do that feature transformation in the quantum space, and then using a sort of measurement with expectation value, right? Using an expectation value, you can converge to your output state in that particular feature space. Okay, it can be a classification where your output for each of the states can be a level, right? Or it can be a clustering where it can actually tell the distance of your state from a centroid of another of a cluster. So these measurements are called expectation values, which we can do by suitable quantum operations, right? After this kernel transformation in the quantum Hamiltonian, right? And we can do these operations, okay, in the quantum domain. And those are the basically supervised means we are trying to assign to a class level, and if we are doing unsupervised, we are trying to define a distance metric by which we define that whether it is closer to a centroid A or centroid B. Okay, and this can be done in the quantum domain. We can actually this operation, as we also say, that in many cases it is a variational quantum circuits. As we are trying to work with the theta, there are number of parameters, okay, of the quantum circuits, and we can actually take all the parameters or some of the parameters in some state. It is a mixed operation. It is not that when we define that it is a u theta, all the parameters of all the gates in that u theta cluster are parameterized. It may be a combination of some parameterized and some non-parameterized gate, but whatever is the case, right, you can use a classical optimization function which can actually optimize these parameters and can feed it back to the quantum system, and you can come up with the most probable or the best probable u theta combination, right, u parameter combinations, right? Okay, and that is called the classical quantum handshaking in doing this, running the machine learning problems, right? And then we can go to our most popular type of machine learning, neural network and deep neural network. Okay, where we can show that this particular operations what we are doing, we can actually do the transformation, what we actually do the weight vector and the bias transformation, right? And then an nonlinear activation function. This can be equivalently defined by an u theta. The weight function can be defined, the weight and bias can be defined by an u theta function, and this nonlinear activation can be defined by a measurement operation. an expectation value operator, right? And then we can actually come up to some value, and then we can go with the pooling and all this type of layers activity, of doing this particular thing. So these are the basic conceptual blocks. Obviously, due to the time limitation, we cannot get into the details of the operator sequence, but I hope that what I tried to pass to all of you is the basic way of viewing that, how these circuits can be built in the quantum domain, right? Right, and this is again there are experiments and there are established works by which we can actually start with a big architecture like convolutional neural network, the weight vectors. The weight vectors can be converted to the U theta operators like this, right? And then the pooling operation is a subsampling, right? It's pooling operation is a subsampling, which means that you are selecting some of the high values and you are rejecting the low values. Those can be converted to a control knot operators. As you know, control knot operators, if you are actually flipping a state if a corresponding state is high. Right, so it means that if you are above a threshold, you are selecting the value, and if you are below a threshold, you are not selecting the value. So these operations can be well done by the control knot operations, and these circuits are also very well established. So you can convert a convolutional neural network using a U theta sequence of gates, and then some control operations for the pooling, right, and then you can go on, right. So this is the way you can do, and then you can have a fully connected network. Also, we can form the neural network, and you can go ahead and you can have the measurement operator, which can give you the nonlinearity. So this is all I think I need to present, and what I try to say is that this is obviously evolving field, the development of the quantum optimizations and quantum ML. We feel that it will have a great role in solving the business problems, right, and also the architectures. The quantum systems will be built to facilitate this type of algorithms, and there are a lot of open problems that there are a lot of research scope is there, right? And obviously the data. So the most interesting part is that we are doing this solutions in a small setting of data. How it will actually scale with the larger size of the data. These are still some of the questions we need to look into, right? And we need to work upon. Noise, already Sushmita ji has said that how error works, and due to the noise, Anupam also said that there's a huge amount of resource we require. So the cost of the algorithms in presence of the noise, because presently we are in the NISQ era. Okay, it is called the noisy intermediate state quantum computing. So this NISQ era is not the fault-tolerant quantum computing. So the fault-tolerant quantum computing means that we can actually reduce the fault to a great extent. Whereas NISQ error tells that you have some error and you have to do some sort of repeated operations or measurements, and you have to work with a small amount of data and smaller circuits, so that you can actually do the quantum computation with an approximate type of solution. Okay, so these are some of the challenges in quantum machine learning. It's a lot of way to go, right? Right, in terms of physical implementation, right? And that's all from my side. Thank you. Yeah. So these are some of the references. You can just pick all the algorithms. What I have said. These are the golden references of all the algorithms. Okay. So now you can go for question answer session. Okay. We all can come up, right? Yeah, so now the floor is open for question answer sessions.
What is the difference between interference and entanglement? Yeah. So how we can implement interference and entanglement? How we can implement interference and entanglement? What is the difference between these two?
What's the difference between?
What is the difference between entanglement and entanglement? And how we can implement? Are there any practical systems where entanglement is implemented?
Yeah, entanglement. Can I go back to my slides? Maybe I'll use this one. The PDF is better.
Entanglement is a state. Right? Interference is on the more on the amplitude. That means actually the amplitude distribution is such that if you increase one amplitude, one will decrease. So there are some special gates which prefers some states. Those amplitudes will be higher, and the other states are not preferred by that particular operation. Yes. These gates are uncovered, and the state and the gate are overlapped, and then it is seen the whether it is modified on the screen.
So remember when I talked about error correction, there was a state which was not exactly equal superposition. So it was a 2-qubit circuit, and in 2-qubit you can have 4 possible basis states. Instead, we had something called a Bell state. In fact, the Nobel Prize for Physics of 2022 went for 2 physicists who showed that Bell states are actually realizable. Okay, so so the Bell state that I showed was 1 by square root of 2, 0, 1, and 1, 0. 0, 0, and 1, 1 were not there. Okay, and there was a circuit which had a Hadamard and a C0 operation. Okay, and with that, if you the inputs are 0, 0, the output will be the entanglement over there. So typically, among the gates, C0 gates are the 2-qubit gates which are entangling or correlating the values of the 2 qubits on which it's operating. Okay, and entanglement in mathematical terms. Superposed states can be separated. That means superposed states can be expressed as a tensor product of smaller dimensional states, right? So equal superposition would be a tensor product of unit dimensional qubits, all n of them. Whereas entangled states are known to be non-separable. They cannot be expressed as a tensor product of 2 separate dimensional circuits. So the advantage of that is that it's kind of, you can think of it as that they are kind of tied up. They have some correlation of their values, and so in this room, if we can have 2 qubits by some pulses and some operations, we can entangle them. We can make them entangled, and then you take away one of the qubits to the other end of the world. But still, if you do some operation over here in such a way that it's the other end also. So entanglement is very important in QKD, in communication. And one more thing, we have been talking about all this error correction, noisy intermediate scale devices, quantum devices. That is all for quantum computation. We get to realize the algorithms. However, as I said, quantum communication and quantum sensors, they typically do not need too many qubits, and they are already in place. People are using quantum sensors, people are using quantum communication channels, as Unpam mentioned. China did that from ground, from Earth to a satellite. Okay, and that is in terms of cryptographers, it's a secure communication.
Yeah, so that is a big problem that we see right now in the cryptography, that we cannot ignore the advance of quantum computing anymore. And even if it is shown on a very simple scale, because we already know the data that's being stored right now, it can be decrypted in a few years' time. So we have to start migrating immediately. So that's a very, very direct impact. For QML and all others, I would say it's happening, but more slowly. You can delay it. For crypto, you cannot.
So this is the entanglement that I showed.
Is there a measurement for this?
Sorry?
Is there a measurement where we can unentangle these things?
Measurement where you do it collapses. Okay. You can, so these it's a reversible. So if you apply the reverse of this, you get an. If that answers. Am I right?
So the trick is that if you measure 0 in a measurement, you know the second qubit is 1. Right? So you don't have to measure the second qubit at all. Right? If you know the first qubit is 1, you can always tell the second qubit is 0. So that's the quantum communication part. You don't need to measure the second qubit.
Yeah, implementation can happen. It's the but still, I would emphasize initialization and measurement involves quite a bit of error. So we are still working. I mean, technologists are still working on those parts. I think all three of us are computer scientists. So the technology part, it was Manush. I don't know whether he's around. He may be he is there, right?
Hi, I'm still around. Yeah. So,
Sure.
so I guess if I can't hear the question well, but if I understand it correctly, the question is about how do one measure this state, this entangled state, right?
So not only measurement, initialization, entanglement, how do you actually implement them? That is the question. You are the right person to ask.
Right. Maybe I start with the measurement because that state was somewhere there on the slides. So if you look at this state, it is what it denotes is the first number is belonging to first qubit, the second number to second qubit, and then we add, and that the second component also has first qubit and second qubit. So you see, when we measure it, we have to measure correlations between first and second qubit. Now, if you remember what I showed before in my talk was that you can see light when it is on, you don't see light when it is off. To measure an entangled state, you will see one light on, one light off in one measurement. Another measurement, you would see the correlated other option. So 0, 1, 1, 0. And by this, you can reconstruct the actual state by n number of measurement at different bases. And that's called tomography of the state. So that's how you measure it, actually. Now, how you initialize it, that depends on the platform. But maybe it was too fast. I also showed that one. In atomic circuits, it is done by what is called optical pumping. So you start all calculations, everything in a quantum computer by initializing everything to 0. Now, there was a question in between that how do you load classical data? Now, the classical data can be encoded in various ways. One way is directly encoding onto the initial state, which means if I want to encode 3, I would then just do 0, 1, 1, 1, and so on. So I would, if I have 2 qubits, I would use 1, 1. So similarly, if you want to encode, you can encode by that, or you can encode in, for example, the phase of the superposition state. For example, there is this somewhere, yeah. So if you generalize this state psi prime, what we see there would be an exponential I phi into the second term. And you could actually encode on the phi your classical data, because that's a real number. So there are many ways to encode data, and it is still a problem, and it's an open problem. How do you upload a quantum computer with a large amount of data? Because there is a finite amount of resource needed in order to encode, and those resources, quantum resource, because you have to perform certain gates to upload it. Now, if you have a large amount of classical data, what is the best way to do it? So that's still an open question. So for example, quantum RAM is not available at the moment. There are some ideas, but not implemented yet.
Any more questions?
Any last minute?
Is temperature the reason why so much noise is predominant? Temperature fluctuations.
Is Yeah, maybe I can take this as well. So, yeah, this is an important question. So maybe we have to look into the frequency, right? So if you take, for example, a superconducting qubit, it operates around 4 to 10 gigahertz. Now, if you take normal temperature at room temperature, it's about, in Kelvin, it would be about 300K. Now, you can convert this 300K to a frequency. And this frequency would be very close to gigahertz, which means if you leave a superconducting qubit at room temperature, it by itself will change from 0 to 1 because it has enough energy from the environment. So that's the reason why superconducting qubits operate at a very low temperature of 20 millikelvin, apart from they have to be in the semiconducting state. Now, for other type of computers, that temperature is not a major issue, but there are other issues like technical noise. It could be a magnetic field fluctuation, could be an electric field fluctuation. So a quantum system is very sensitive to any of these.
Thank you.
One thing I must add is that we are not going to have quantum computers replace our CPUs, our general purpose computers. We will use quantum computers only to solve problems, so they could be like coprocessors or subroutines, to solve problems which will give us significant speed up in time, maybe exponential, maybe super polynomial speed up. Only for those we will use quantum computing. You can imagine that although resources are expensive, keeping them at those low temperatures is also very, very expensive. You won't have a quantum computer on your desk.
For boosting the speed up of your thing. Boosting the speed up and performance of your
Speed up.
Intel is trying something.
Yeah, Intel along with TU Delft, they are trying to have CMOS-based quantum dot technology. Maybe Manush can tell us if he's there. Manush, would you be able to?
Sorry, I did not follow the question. The sound is not very good.
So that Intel
Can you please repeat?
The CMOS and quantum eliminators.
Sorry, can you repeat it, please?
Hello, can you hear me?
Yeah, I can.
Can you hear me now? Yeah. So the discussion here was on, I mentioned that we won't have quantum computers on our desktops, and it's very expensive to have those low temperatures. Intel is working with TU Delft to come up with a CMOS quantum dot kind of a solid state quantum technology. Could you just illuminate us on that?
I see. So Intel is working on a few things. So they were working with TU Delft also on superconducting circuits. The electrode-based, on silicon, there are few possibilities. One is called silicon donor, which means you at a given site, you add one more electron. And if you add one more electron, this electron kind of gets trapped in the silicon wafer. And then you can use its spin for a qubit. That's the kind of platform that Australian group Michael Scheinman is following. Yeah.
Right.
In TU Delft, there is a CMOS kind of activity, but one has to see these very carefully because the current development is not scalable at the moment. Yeah, and the reason behind this is the material. So we know very little about the material, and one has to understand that these pins or these qubits actually reside within a material. So any impurity close by will spoil the qubit because any impurity nearby would also act as a qubit. If you have an acting qubit which is uncontrolled, then your information is lost. It's a two-state problem. It is a very well-known problem. And that's the reason why Intel is one of the places where you get very high purity silicon wafer. Um, but even then, it's, I think they are under 9 nines. But even then, it's not good enough for running quantum.
Right. Into Delft, what's his name? Veldhorst. He is collaborating with NU and into Delft. His group has been working on coming up with solid state. But yes, you are right. The purity part is a very challenging thing and very hard to control also.
Yeah, I mean, well, I work with atomic systems, therefore maybe I'm a little biased, but in general, I know that the field, even in superconducting qubits, it's very difficult to actually control the breaking property.
Any more questions?
Can you shed some light on post-quantum cryptography?
Post-quantum cryptography.
Yeah. So in general about the post-quantum, so the okay. No. So that is one thing as a misconception. The post-quantum crypto algorithms are actually implemented on classical computers. They are not implemented on quantum computers. But the algorithms that they are based on, for which there is no efficient quantum algorithm.
The mathematics behind that is different from what is in the other earlier versions. It's more, very deep mathematics goes into it to ensure that the operations required are difficult.
Like for RSA or ECC, you have this factoring and discrete logarithm, for which we have very efficient quantum algorithms. So we can break this. But for post-quantum cryptography, those are based on other concepts. Like these are based on code-based cryptography, based on hashing, based on lattice problems, for which there are no efficient quantum algorithms as of now.
So till date. Come up with them.
Yes.
He will repeat a shot.
So it resists a quantum attacker. But these are implemented on regular.
So the classical algorithms, but which can resist quantum attacks.
And how much classical compute power do these PQC?
Comparable. So the overhead is not much.
So that's the plus point.
Yes.
I think we can call it a day.
Yeah, right.
Thanks.
Okay.
Oh, you have
Thank you.
Quantum computers are connected in number and controlled by only big player. Then who is going to break this ECC and whatever you are calling this cryptography?
Sorry.
No. Quantum will be offered as a service, na. So they can push their task to the cloud, na, quantum cloud.
No. My question is.
Can you use the mic, please?
Who will break?
Yeah. So my question was, if there are only limited number of quantum computers available in the future, and that those are controlled by the big players.
We cannot tell. Present you can tell.
Yeah. So present or maybe in the further future, then who is going to break this RSA and the ECC?
So all these quantum computing are supposed to be available over cloud. So, and if you are a registered user of that quantum computer, let's say IBM Q, you can even register today. You won't get too many qubits, but later on when they allow, you will have maybe a lot of qubits. And yeah, you are right. Whether IBM Cloud is going to monitor your activity or not, I don't know. It's going to be very difficult because all you will be doing is, factoring something.
Yeah. How you can tell that?
You're running Shor's algorithm.
But that's only some maybe less than 1% of the people using this, right?
So can I take this question?
Yes, sure.
Yeah, this is a nice question. I could not leave it. Yeah? So the thing is, I mean, it would be very naive to think that IBM will be open when millions of qubits are available for breaking codes, right?
definitely there would be import restrictions and everything in place, right? So then every country will block it. And as we know from the atomic bombs, of course, nothing could stop it from being pirated from one place to the other. And so which means it would be available to certain countries while disadvantaged to other countries. And it might happen to corporates through the countries. So it's not going to be like everyone can break everything, yeah?
But still, the possibility remains. Okay, then thanks a lot for your attention and your enthusiasm. Thank you.
Thank you. Thank you. And definitely a big thanks to all of you, all the presenters, for such a great enriching learning experience that you have given through this tutorial. Thank you so much. And also we would like to as a small token of appreciation, right? We would like to hand over a small memento. Thank you. Thank you so much.
Thank you.
And just would like to also thank Dr. Manas. We know he's not well, but still he took time to actually attend the session and give his valuable part of it. Thank you, Dr. Manas. Thank you. And also would like to thank Dr. Robert. Yes. Would like to thank Dr. Robert. I think he just logged off, but yeah, thank you. Thanks all the speakers. Thank you. And thank you, audience. Thanks for joining the session.
Yeah, so he can take it. He will be going back to Singapore.
రేపు నేను ఉన్నాను అట్లా నేను లీవ్లో ఉన్నాను.
The issue is that once you have the system there, once you have the algorithm, right, you cannot say that who will use the system and who will run the algorithms. Yes. Problems to look at. No, you can't tell like that. Nah? If there are systems, if there are algorithms, people will use it.
Okay.
People will use it. Right. So hackers also uses some systems, right? So you don't studying all this, right?
Then one day
you
come and say that this is going to
Oh, he has worked a lot on the classical cryptography.